Right, good morning everybody. And I think we had yesterday a really successful day. Amazing talks, little break in between, and also lively discussion at the posters. And I think everybody, all the presenters, people who gave the talks and posters, they also deserve now an applause from the successful yesterday. And yet today we have a full conference day, more exciting talks. We will start with Will's keynote in a minute, and after that we will have a session on fabrication and materials, because we thought that if you don't have good chips, there will be no good quantum computers. So this is extremely important for the field, and it's good to be on track. What are the best practices there? And for good quantum computers, you also, of course, need to implement good high-fidelity gates, readout, and reset. And this is the following session then after that. And then comes the algorithms and applications session, because we didn't not only want to be like only hardware conference, but we also wanted to welcome those who work on algorithms and applications related to superconducting quantum computers, of course. And then the last session will be on millikelvin electronics and other supporting technologies. We know that we need that. We need that to scale up the quantum computer in the future. We can't just make everything bigger and bigger and bigger so that we need also better solutions for there. So that's for the day. And as I said, we will now begin the day by a talk by a very renowned person in the field, our friend Will Oliver from MIT. So please, Will, come on stage and tell about these giant artificial atoms that you have been working on at MIT. So, Will.
Yeah, thank you very much. It's really a pleasure to be here, and I was happy to, help to organize the conference. But really, a lot of hard work was done here, and I want to acknowledge that hard work. And I've really enjoyed the conference so far. And also want to mention that I may have made a small mistake, which is that I remember when Mikko first asked me to give a talk, he said you should talk about materials and fab, and I'm in a materials and fab session. I will have a little bit on 3D integration towards the end, but I forgot that we had that discussion. So what I would like to talk about still has to do with extensibility and scalability, and that's related to a scientific topic, which is the title of the talk, which is Giant Artificial Atoms and Waveguide Quantum Electrodynamics. And I hope to make a connection between this seemingly scientific talk and something that I think is going to be very important as we scale up quantum computers, and that's going to be modularity and remote communication. So let me get into it. Before I do, I'll acknowledge at the end the team members at MIT campus and MIT's Lincoln Lab, but I also want to acknowledge Anton and Franco, who were theorists that we collaborated with on this project. So we often talk about qubits as artificial atoms, and so when we say atoms, we usually think of what I'll call small atoms to contrast with large atoms. So small atoms just means the atom is itself small compared to the wavelength of light that's driving it. Okay, so you can think of polarization of an atom, the charge fluctuating, say, in an electric field, and it basically follows the wave that you're using to drive it. And if that's happening, then we'll call that a small atom, or just an atom. And when you do that, you can use the dipole approximation to describe how the atom responds to that field. Okay, and that's the way we usually learn it in physics. And so we'll equate dipole approximation to point-like atom. And we can then look at different types of atoms and systems to see how this bears out. So for a natural atom with optical light, we're talking about angstrom scale. The wavelength that we drive it with is 1/10 to 1 micron. And so the ratio of these two sizes, 10 to minus 3, 10 to minus 4. Okay, so that's really a point-like object compared to the field that's driving it. It's even better with Rydbergs. With Rydberg atoms, 10 to minus 7 or 10 to minus 8 is the extent. But we drive them with microwaves, and so as a result, now the ratio of the radius to the wavelength is 10 to minus 4, 10 to minus 6. And it's also true generally with our superconducting qubits. And with these length scales, 100 microns, and again, microwave light, then the ratio there is 10 to minus 2 to 10 minus 3. So these are, in fact, artificial small atoms. But it need not necessarily be that way. We can in fact, design giant atoms with our superconducting qubits because we can extend them beyond a point-like object. And when we connect our superconducting qubits to, say, a waveguide at multiple points that are well separated compared to the wavelength, or on the order of the wavelength, we now have a giant atom, and we need to think about quantum interference of emission and absorption between those two pathways at those 2 points. So we need to think about the phase delay that's there. Okay, and that's what we're going to leverage in this work. So I'll start with an outline, waveguide QED and giant artificial atoms. I'll then talk about directional photon emission, where we can selectively send a photon to the left or to the right. And then at the end, I'll talk a little bit about lattices and 3D integration, material science. And let me acknowledge here Bharath and Dan, who really were fundamental in doing this work. So we all know cavity quantum electrodynamics, because that's the way we have been working for the past 10 years in this field. It's the dominant architecture. The cavity is there to protect the qubit or the atom from its environment. Basically, by putting the cavity there, you reduce the number of modes that the qubit can interact with. And then we detune from those modes and the dispersive limit, and now we're protected. And this can be used for control as well as readout. I think these days mostly doing readout this way, but you can also do control by driving through the cavity. Waveguide QED is different. It's ideal in some sense for studying dissipative phenomena because, in fact, this is what we tried to avoid by doing cavity QED, right? If you couple an atom directly to a waveguide, say a 50-ohm coax, you have a quasi-continuum of modes, each of which is ready to take the energy away from your qubit, right? So in some sense, you wouldn't necessarily want to do this. We tried to get away from it early on. But you can use it to release and absorb quantum information, and that's how we want to use it here. So the challenges, though, of trying to operate in this regime is that there is this always-on dissipation, right? The qubit can very easily emit its energy to the waveguide. And so you might try to come up with some way to tunably couple to that waveguide, turn it on and off, and then can we engineer interactions between two qubits along the waveguide? Those are basically the challenges that we have to face if we want to use this waveguide QED architecture. We're certainly not the first people to do it, and I won't read through every entry on this slide, every panel, but you can see that, going back more than a decade with Astafiev et al. At NEC, and following on since then, a lot of work out of ETH and Andreas's group, on to work very recently, even Oscar Painter, for example, Chris Wilson and others. There's been a lot of work in what you might call waveguide QED or even microwave quantum optics, and we've leveraged that work very heavily in ours. So waveguide QED with superconducting circuits looks something like this. Let me see if I can get a pointer here. So you have a waveguide. Think of it as a coplanar waveguide on a chip. 50 ohms, let's say, and we couple to it these, here it's 3 qubits with frequency omega. We'll talk about a coupling rate between the qubit and the waveguide as gamma, and of course, that's to the waveguide, but our qubits still have other channels by which they can lose energy, and we'll call that non-radiative decay, so gamma NR. This is what it looks like in a circuit schematic. If you have this 50-ohm transmission line and the qubits here, we'll use transmons in the usual way, tunable transmons. And this is what it looks like on a chip, where the gray area is metal, in this case aluminum. The white area is a bare field of silicon. And here's the qubit coupled to the waveguide. The qubit itself is, this small squid loop here, and we drive it with a B field through a on-chip antenna that you can see. Okay, so when we couple atoms, now we're talking about natural atoms, to propagating photons in free space, there's very weak coupling generally, and it's because the atom is, again, point-like compared to the field that you're using to drive it. So it's a small cross-section. And in fact, there's poor spatial mode matching in the jargon, right? Because you're driving with this plane wave field, but then the atom emits spherically, okay? But if we work with a one-dimensional waveguide, it just means that there's one long dimension, everything else is confined. It's a different story, and we can get much stronger interaction because we confine the light, and of course, with artificial atoms, things are much stronger. So we can send in a tone which drives our superconducting qubit from ground to excited state, and then when it emits, it basically can only emit to those original modes that we use to drive it. Okay, and that's quite different than in free space, where you get this complicated interference pattern between the light that we're using to drive the qubit and the emitted light. Whereas in our case, with 1D channels, right, what happens is that in the limit that we're driving weakly, what does that mean? That on average, there's much less than one photon on average, that the forward propagating light destructively interferes, and the reflected light constructively interferes, and that's how it works in this system. So we can think about cooperativity, and usually we think of that in terms of a cavity enhancement factor with the overlap matrix element of the electromagnetic field, but in a waveguide, there's no cavity. So that basically is one. That term isn't there now. And so we really just have the electromagnetic field overlap. But again, in this one-dimensional system, it can be very strong, and that's why we can actually do this. So, of course, we want the rate of emission and absorption to and from the cavity, to and from the waveguide, to be much stronger than the non-radiative relaxation. We want our qubit to have a long T1 compared to the time it takes to exchange energy with the waveguide. Okay, so what does spectroscopy look like in the system? Well, you can just do it with a network analyzer. We hook it up to the input of our device package, has this 50 ohm waveguide. The qubit is somewhere along the waveguide, and then there's the output. And we use a large attenuation so that we can get down to the single photon limit. Okay, so this is what we see is, again, this, as I just described, the absorption and emission in such a way that the reflection is almost perfect and complete, and the transmission is almost zero because of destructive interference. And that's borne out here. Here's S21 versus the detuning with respect to the qubit. So when the tone is on resonance, you can see that the S21, the transmission, is better than 10 to minus 4, so very, very small. Okay. This is what it looks like if you exercise all the parameters. So here's the detuning on the horizontal axis and the power on the of the drive on the vertical axis, and you can see when the power is small and we're on resonance that the transmission again is zero, as we expected. But if you start to drive more and more strongly and increase the probe power, basically what's happening is your field gives the atom a photon and it gets excited, but then another photon comes along, the atom can't respond to it, and that photon just goes through, right? And so as you turn up the number of photons and they arrive at too fast a rate, most of them just go through while the atom is busy absorbing and emitting its single photon. Okay, so that's what this is showing here. And this is what was first demonstrated back in 2010 for superconducting devices by Oleg Astafyev. Okay, so we can look at how we do measurements here. And this is a detail, but an important one, that if you just want to measure the voltage that at the output of a Fock state, of course, in the IQ plane, Fock state is spherically symmetric, so you don't measure anything, right? So you have to measure something else. Here we're measuring along the x basis, so a superposition state of 0 and 1. And when we measure the voltage at room temperature, it will oscillate, as you see here, as a function of time. Had we used, say, the z basis, put the qubit in its excited state, it emits a photon. Now there's no relative phase, it's just not there. We measure 0, right? And that's because there is no signal in the IQ plane that we can resolve with a Fock state. So we measure along, long story short, we measure along the x basis here. Okay, and when we make that measurement, there is the voltage signal at room temperature from the emission of the qubit, the photon emission. We also use a windowing function to shape it, because there is this decay here, and we want to capture the strong part of that decay, so we window it appropriately. And then there's some gain, and we measure something at room temperature. But what we measure at room temperature has to be converted back to the photon that's emitted at the qubit, and so this requires calibration. And I won't go into that today, but you can imagine that that's true. And we also need to account for added noise, right? And so we do that as well. And the approach that we use is based on Christopher Eichler and Andreas Wallraff and company from ETH, and those papers are shown here. Okay, now, having a single qubit on a waveguide is important, but we would also like to do qubit-qubit interactions along a waveguide, and you might ask, how does that happen? So, of course, we can take our two atoms and we position them on the waveguide a certain distance apart. Let's imagine that we position them one wavelength apart, where the wavelength corresponds to the frequencies of the qubits, and the qubits are degenerate in frequency. And of course, you can emit, or a qubit that's in its excited state can emit a photon at its frequency. Can also communicate with the other atom via virtual photons, which is over some short period of time emit at a different frequency and then have it reabsorb. Okay. And as long as it protects the time frequency uncertainty, then that can happen. And what we find, though, is that if these two atoms are spaced by, for example, a wavelength or multiple of a wavelength, there's basically destructive interference to these virtual photons. And just to give an example of what that means is that I'm showing here a red detuned and a blue detuned photon. So not quite on resonance, not quite exactly a wavelength. And of course, they come in pairs. If you're detuned by some amount at positive frequency, detuned by a negative amount, you can take those two photons, the virtual photons, and ask what happens. The coupling, of course, goes as the couplings to the waveguides G and also the detuning from the qubit. And there's a little table here. So one is positively detuned and one is negatively detuned, and we'll assume that they all have basically the same coupling to the waveguide. But what you see is that one comes in with a plus sign and one comes in with a minus sign, just arising from this plus and minus detuning. And so by pairs, they all destructively interfere, and when you integrate over all virtual photons, nothing happens. Okay. And if that were the end of the story, it wouldn't be very interesting. But you could space these by 3/4 of a wavelength instead, or some multiple thereof. And now you have, again, the real photons, which look like qubit decay, but also the virtual photons, which lead to the exchange interaction. And now we have a constructive interference, and you can see that from this table again. And again, you have positive and negative detuned pairs of photons that are virtual. But the difference here now is you have a negative sign in the coupling, and that just basically arises from the fact that now the red detuned one, at the qubit, spatially is negative compared to its partner, which is positively detuned. So that coupling also carries a plus and minus sign, and so now everything is positive, and when you integrate over all these modes, you get a net effect. All right, that's what we rely on. And so the positioning, the upshot here is that the positioning of the atoms along the waveguide matters quite a bit in terms of how the coupling happens. And when you do that integration, you'll find that the net coupling between qubits goes as gamma over 2, where gamma is the emission rate to the waveguide, times sine phi, where phi is the phase represented by the separation. Okay, and we'll see that in just a moment. So here's the design or the device geometry of two qubits. So you have two giant atoms, qubit A and qubit B, connected to the waveguide at 2 points, well separated on the order of a wavelength. And between each of these 2 points, the distance corresponds to a phase phi. We just chose it to be that way. Here's what it looks like on the layout. You can see the input and output of our 50 ohm waveguide in blue. There are 2 qubits. They'll pop up in a moment right here. This yellow piece is the capacitor. You can see where the waveguide connects to it at 2 points for this qubit, the drive line, and then we also use a conventional readout here. We can read it out using the photons, but it's convenient experimentally to also be able to read it out in the usual way using cavity QED. Okay. So let's just look at one of these qubits for a moment. We'll detune qubit B and just focus on qubit A, right? So remember, there was a phase difference of phi between qubit A and where it connected to qubit B, and then another phase phi coming back to A. So the round trip here is 2 phi. Okay. And if we measure T1 of this qubit, its relaxation rate, you can see that it depends entirely on the bias or the qubit frequency of qubit A. We'll tune the frequency of qubit A and ask how T1 varies. And the decay rate, 1 over T1, varies in this way, and it has a minimum, meaning that the T1 is longest, corresponding to this decay here, shown in the, and it's about 30 microseconds. And that's basically, for this qubit, the decay time if it wasn't coupled to the waveguide for this qubit. And so what's happening is that due to constructive and destructive interference, we're able to change the rate at which the qubit emits to its environment, to this 50 ohm environment here. And this omega df stands for decoherence free. This is a point that we can bias the qubit where, due to destructive interference between emitting and absorbing photons at these 2 points, the qubit no longer emits a photon to the environment at that frequency. Okay, so that's a very useful feature. Okay, and you can see the formula up here. Okay, so now we can talk about 2 qubits coupled to one another. And again, it's this same configuration, but now the coupling between qubits at different points goes as this gamma over 2 sine phi that we talked about a few slides ago. And that happens between every pair of points. But then there's one additional pair, the outermost ones, which are separated by 3 phi. Okay? So those are all the contributions. We add them up coherently to get the net coupling between qubits A and B. And we can now detune and then bring those 2 qubits onto resonance. And when we do, we get an avoided crossing with a strength G given by this formula. So we can bias these qubits in such a way at frequency that they're degenerate with one another. They're separated by this 3 lambda over 2, and they can talk to each other via the waveguide. Okay. So then, of course, you want to put these 2 facts together, and you can. And what you see is that we can bias the qubits at the decoherence-free subspace. So individually, they don't emit to their environment, but at those frequencies, they can still talk to each other. So that's very convenient. We basically turned off the 50 ohm environment, but we still allow the qubits to talk to one another. And we can do that by design. Okay. So there are many ways that you can design this. You don't need to necessarily couple at 2 points. You could couple at multiple points. And so the decay rate, for example, as a function of phase at 2 points has this 1 minimum. But if you couple at 3 points, you can have 2 minima. And if you couple at 4 points, you can have 3 minima, and it works like this. Okay, that's one thing you can change. Another thing you can change is how strongly, let's say you're coupled at 3 points, you could change the relative strengths of the individual couplings to the waveguides. That's another knob that we can tune. And since it's 3 points, there's 2 minima, but changing the relative strength changes the, if you want to think of this as a double well, it changes the properties of the well, of the barrier in that double well. Okay, and then of course, how we position the qubits along the waveguide, we already talked about how that matters. So there's a number of design parameters that you have at your disposal to use and design these qubits. Okay, so let's take an experiment that we did where to demonstrate the coupling. Each qubit is now coupled at 3 points to the waveguide. These are giant atoms. The phases are shown down here. This is what it looks like on chip. Again, blue is the waveguide, and now if you zoom in, you can see that it couples to each qubit at 3 points, as we say. Okay. In terms of numbers, just to show you, these are the phases, the separations, and then also the strengths of the couplings at different points is intentionally chosen to be different. Okay. So if we look at the resulting decay rate, we can see now that there are 2 minima. We'll call it decoherence frequency 1 and decoherence frequency 2. There are 2 places we can park the qubits that are not degenerate, but each individually don't emit to the environment. And then we can also look at the coupling between qubits, and the coupling between qubits when they're degenerate, not when they're separated, but if you bring them onto resonance with one another, in the red shows the coupling strength. Okay, and you can see that the coupling strength is fairly strong at each of these decoherence-free frequencies. Okay. So this was the experiment that we did to demonstrate this. We have 2 qubits, A and B. Each one is parked at its own decoherence-free subspace, non-degenerate, so they don't talk to each other. They're not interacting. They're just sitting there, but isolated from the 50 ohm environment. We do a pi pulse on one of them, and then we bring qubit A on resonance with qubit B. They're now both sitting in the same decoherence-free frequency, and because they're resonant with one another, they exchange, they talk with each other. Then we do readout. So the swap or exchange interaction is shown here, and when it's yellow, it's black, and vice versa. So it's exchanging energy, and taking a slice at 0 detuning, this is what it looks like. And of course, we'll pick the point where we can get a superposition, or in fact here, an entangled state. So the entangled state that if we time it just right is this 0, 1 minus I, 1, 0 state, Bell state. And then when we do tomography of that state, we find the fidelity is 94%, which isn't necessarily a world record for cavity QED, but for waveguide QED, this is almost unheard of, right? Because in general, if you couple your qubits to a waveguide, you'll lose the photon within 5 or 10 nanoseconds. It's just gone immediately. You don't even have time to do the pi pulses generally, right? But with this waveguide QED giant atom approach, as I've described, you can actually decouple in a way that you have time to do these operations and then selectively emit when you want to. Okay. So we can entangle qubits despite the strong coupling to the environment, and that's quite useful. Okay. Just a few notes here that I want to highlight is that this is also interesting from the perspective of doing some experiments with multiple qubits. For example, an Ising spin chain with nearest neighbor interactions or all-to-all interactions along a waveguide. I won't have time to go into it, but this is work that Anton has done and published here back in 2018. Some of these geometries are possible within a waveguide QED environment. Okay, so getting on to something that may be closer to extensibility and interconnects, we know that we want our qubits and processors to be modular and extensible. And so we want to be able to distribute entanglement between distant locations. Of course, one way to do that is to convert to optical photons, take things out of the fridge into another fridge. Okay, that sounds really hard. It is hard. People are working hard on it. But you could keep it in the microwave regime, but you need a good way to exchange microwave photons between chips. So you want to have some kind of quantum interconnect just with the superconducting qubits, and this has been done by a couple groups now. You can couple via cavities, right? You could just have a cavity and multiple qubits coupled to that cavity, and they exchange energy, no problem. They have high fidelity. In fact, they're bidirectional. You can go both from 1 to 2 and 2 to 1, but there's a limited node connectivity. You can only connect so many qubits to those waveguides, right, or to those cavities. You can couple via single-ended waveguides, and beautiful experiment from ETH has done this over very long distances. So it's versatile, but in many cases requires a lossy element like a circulator or an isolator. Maybe someday we'll learn to do that without loss or with low loss. But generally, it's this is basically one-way communication. Okay, so you'd like to sort of take the best of both worlds. So the goal is bidirectional communication with itinerant photons, traveling photons, on a waveguide that goes in both directions. And you can communicate in both directions. So the platform will be artificial atoms in a waveguide QED environment. So the module that we envision has 2 resonant emitters, and their only job is to emit and receive photons. And then they connect to their own quantum processor on the same chip. And when you want to communicate with another module, you take information out of your processor, put them into these 2 qubits, and you emit to the right or to the left. You choose, right? And then another module picks that photon up, and through that you can do remote entanglement. So here's what the experiment looks like. We have 2 qubits, qubit 1 and qubit 2. We'll put them in this entangled state here, EG plus e to the I pi over 2 GE. And we couple them to a waveguide. And the separation is shown here. It's a lambda over 4 in this case. And you can, of course, this state will emit to the waveguide. And you can tabulate what's going to happen. So let me step through the different possibilities. One possibility is that, in fact, qubit 1 had that excitation, and it emits to the waveguide and emits to the right. And there are 2 phases that show up. One is the state of the qubit, its phase, and okay, that's here, we'll just call that 0, e to the I 0. And the second is its position phase. We'll reference everything to this left point, x equals 0. So the relative phase in front here is shown. Second possibility is that qubit 2 was in fact excited, and it emits to the photon. It emits its photon. So its phase is pi over 2, right, from the original state. And its position phase is now located pi over 2 away, and we're defining minus to the right side. Okay. And that's if you emit to the right. If you emit to the left, it's a similar story, but what you find is that for this particular phase pi over 2, these destructively interfere, and it doesn't happen. So what's left is what constructively interferes above in gray, which is that the photon goes to the right. No photon goes to the left. Okay. Now, there's one other detail here that's important, and that is that I neglected to mention that, of course, these qubits are also talking to one another at the same time, right? That's a coupling via the waveguide that we just saw, but we don't want it, right? So what we do is we put a tunable coupler in between these two qubits and exactly cancel that coupling. So we, using a physical tunable coupler and couple those two qubits with a, opposite sign so that any coupling via the waveguide is canceled. All right. Similar argument, if you change the phase to minus pi over 2, now the photon destructively interferes to the right and it constructively interferes to go to the left. So just by choosing the phase of the emitter qubits, you can select which direction the photon will go. Okay. So the emitter module that we imagine for this node looks like this. You have, of course, your two qubits I just talked about coupled to the waveguide. And then we're going to use in this demonstration two other qubits that represent a processor. It doesn't need to have two qubits, could have 100 or 1,000 qubits, whatever. But we'll use these two at the beginning, and we have tunable couplers between all pairs here. The idea is that we'll use this top one to create the entangled state. We'll then use these tunable couplers to shuttle it down to the emitter photons, and then it gets released. Okay. This is what the device looks like. You can see the 4 qubits. This is in the XMON style, and then the ones on the bottom are the plunger style. And so the first thing we do is we'll put one of the qubits, say qubit 3, in an excited state. We then parametrically drive this coupler to create the Bell state that we wanted. We'll then swap those with these parametric couplers. That state gets shuttled down to qubits 1 and 2, from which they emit quickly into the waveguide. And it's released. Okay. So when we do that with the proper phase, we see that we get emission in one direction to the right, in this case, but zero emission to the left as a function of time. We're looking at the amplitude of the emission. Now, you remember, we're measuring voltage here. So again, we have to create a superposition state. We have to measure effectively along the x-axis. That's why this state is here, but the psi plus is the one that's going to emit. And this is an artifact just so that we can measure the voltage. If we change that phase to a minus sign, then now the photon goes to the left, it doesn't go to the right, right? So this is basically just showing what I described, but this is now in experimental data. Okay. And again, I just emphasize that we're measuring the voltage, and that's why we need to use this superposition state, ground, plus the entangled state that we desire. You don't need to do that, and in fact, you wouldn't do that in an application, but because we wanted to measure the voltage, we do that as an experimental detail. Okay, so when we do the tomography of this, you can see that the tomography looks good. When we intend to send the photon to the right, that's what happens. The correlations are basically 0. When we intend to send it to the left, that's what happens. You can then correspondingly get a fidelity out 98%, 97% for directional photon emission along a waveguide. Okay, so our plan next is to absorb that photon, and Aziza is working on that right now. But the vision is that you would have not just one of these nodes, but many of these emitter-receptor nodes, in your quantum computer, and it would emit and absorb photons so that you can connect different nodes, right? One end goes to your quantum processor, the local 100 to 1,000 or more qubits, and then the other end is coupled to a waveguide. And this waveguide need not just it's a 1D waveguide, but it can snake around and go wherever it needs to go, right? And if you want to emit and absorb a photon, you just detune or bring on resonance the qubits that you want to connect, or the nodes you want to connect. And so these two are detuned, for example, and the node on the right emits and the node on the left absorbs. Okay, so this is the idea, and we're at the point now of demonstrating the absorption. So in the last few minutes that I have here, I just want to talk about lattices and where we're going and the 3D integration and its importance. So if you if we just take a snapshot of where we are today, the Ramsey times are around 100 microseconds, and our single qubit fidelities are, 3 nines and something. 2 qubit fidelities are almost very close to 3 nines. And we're currently measuring chips with 9 and, in fact, now 16 qubits. And you can see these long wire bonds here, which, of course, we don't like. And that's because we just can't fit more lines in laterally. And so what that means is we need 3D integration, and I'll get to that in a moment. We are measuring now 16 qubits in a 3D integrated geometry. On a 9-qubit chip, 3x3, we've done random walks in 2D, and you can think of how we might quantify that as a walk across Manhattan where, the roads are all basically perpendicular to one another. And so if you make an excitation in the lower left, you can count the number of steps that you would take to get to the upper right. And so those lines indicate equal numbers of steps. So 1 step, 2 steps, 3 steps. And so if you do a random walk, make an excitation in one, and then track through this Manhattan distance how the excitation ebbs and flows, it goes to the other side, and it comes back, and then goes to the other side and comes back. That's the experiment, and the simulation's on the right. So this is a Bose-Hubbard model. What we've done is just couple these qubits directly. There's no tunable coupler here. And I won't go into much detail on this here, but what I'd like to say is we're operating this now in the hardcore boson limit, where the interaction U is much stronger, the on-site interaction U is much stronger than the exchange interaction J. Okay. So we've done a number of experiments that I won't have time to talk about today, including out-of-time ordered correlation measurements, and we're working on a 16-qubit array. But what I would like to do is just say that we've done some localization experiments using a disordered lattice. And one feature of superconducting qubits is we have access to every individual qubit. So we can tune the on-site energies explicitly and read out each qubit explicitly. And that is an advantage that we have over our natural atomic systems. So we've done Anderson localization in 1D and 2D as a function of the disorder strength. We've also looked at Wannier-Stark disorder, which is basically just a gradient type disorder, which leads to block oscillations. And I'm purposely going quickly here in 1D and 2D because Amir Karamlo is here, and he's a graduate student in Equus Group, and he's got a poster, so please go check it out. He'll tell you all about these experiments. In the last minute or so, I mentioned that these wire bonds here are problematic, and so we need to 3D integrate. And we're currently, through a generous donation from Keysight Technologies, building a 64-qubit testbed, and I hope to have that going in the year or so. Slowed down, of course, by COVID, and but very generous donation from them. We appreciate that. And that's the refrigerator where we would like to test some of these devices. But we need to 3D integrate because we can't get all the wires into the middle of the chip. And then when we go to 5x5, it's just not going to be practical anymore. So already on the 4x4 chip, we're doing flip chip. And our approach looks something like this. There are 3 layers: the qubit chip, the interposer, and the readout and interconnect layer. And these are 3 different functions, and we separate them out because fabricating them has very different fabrication requirements. And it's easier today to fabricate them separately and then connect them together rather than doing a monolithic process. Someday we may learn how to do it monolithically with high coherence, but today this is the approach that we take. The qubit chip and the interposer are both made from intrinsic silicon in our approach. And so what that means is the qubit and its C is a very high Q material. The qubit has a large mode volume because we make the capacitor large. We do that to reduce the effects of 2-level systems, but we don't want to put another interface right next to it that's lossy, right? So we choose our interposer to be made in a way that it looks like a qubit chip. That gives us another surface to work with, and those could be qubits or those could be tunable couplers. And so that is also an advantage. We now have 2 faces that we could use. Through silicon vias that are superconducting are also very important. And then this bottom layer is a multi-wiring layer, so 8 to 10 layers made from niobium. So just some pictures. This is the qubit chip on top that gets flip chipped over. The TSVs are shown here. This is about 200 microns deep, 10 to 20 micron diameter. Tinitride is superconductor, and it superconducts around 2 or 3 Kelvin, and we line them that way. And then finally, this multi-wiring layer niobium process. Again, the picture I'm showing has 8 wiring layers. M stands for metal. And we use this, in fact, to make our traveling wave parametric amplifiers that maybe some of you have heard of. But it, of course, has junctions to do that. Those junctions, in fact, can be used for other technologies like classical digital superconducting electronics. We don't do that yet, but we do that separately just for classical digital applications. So with that, let me finish, because Mikko stood up. So I'd like to acknowledge people both at Lincoln Lab as well as the MIT campus. Very large teams have helped to make these experiments possible. And I thank you for your attention.
Thanks, Will. Thanks a lot for the amazing talk. And now there is still time for questions, so please ask from giant artificial atoms, photonic modules, the lattices you talked about. Who would like to? Yep, there's a question.
Somewhat quick question on the 3D integration. If you put the amplifiers also on where the qubits need to communicate, won't, like electrodynamically, this is going to get busy real fast, right? So like, how do you make sure that you have a microwave clean environment?
Yeah, so that of course comes down to good electromagnetic design, right? And so that is a key consideration for sure. But one reason we put this interposer in between the qubits and where the traveling wave parametric amplifier resides, or other, signal routing, basically, is that we can move it away, right? And now that makes this task of electromagnetic isolation a bit easier. Doesn't eliminate it, but it makes it easier. Much better than if it's right up at the top face, right next to your qubits, right? Yeah.
Right, more questions. There. Okay, let's take them from there.
Hey, great talk. So typically these tubas have a little bit of reverse gain.
I'm sorry, can you remove your mask by chance? Thank you.
Sorry. Typically these tubas have a little bit of reverse gain, which can be, amplifying just a little bit of vacuum noise and populating the cavities. How do you plan on dealing with that here?
Yeah, so a colleague of mine at MIT, Kevin O'Brien, fantastic professor, and he has some very good ideas about how to design the tuba in a way that mitigates or even eliminates this reverse gain. And so he's published some papers on this, and he's now at the point of testing those ideas.
All right, Matti, next to.
Thank you, great talk. I have a question. At the end of the giant atoms, there was a Rabi oscillation plot, and it showed some damping. So is that only by the internal decoherence, or is there some states above where it's excited, or is it not?
I'm not sure I know which plot exactly you're talking about, but there is, of course, this non-radiative background decay that is always happening, and that will happen at the rate of an isolated transmon. So that is, of course, happening in the background. In these experiments, that was around 30-ish microseconds, whereas the interaction with the waveguide is much faster, 5 to 10 nanoseconds. But there is that background that is happening. That's right.
All right, let's take one more question, Christian.
Maybe I can just ask the question. So regarding your TSVs, why are they in pairs and why are they round? Why are they not round?
Okay. Yeah, so they don't need to be in pairs. We like to do that early on, I think, from a yield perspective, but turns out the yield is quite high, and so maybe it's not so necessary. Why it's a racetrack is, I think, an fabrication detail that the experts have told me, and I believe them, that that's a good idea. So that's...
Great. Well, let's thank Will again. And then we're heading to the session of fabrication and materials that is chaired by Vesterinen from VTT. Visa, please take it away.
Thanks, Mikko. So I'm a senior scientist at the VTT, and also the first speaker of the session, Govenius. He's a research team leader there, and he will be talking about Qubit-compatible 3D integration methods for large quantum processors. So Jonas, please.
Yeah. Good morning, and let me first of all thank the organizers for this great opportunity. It's really been a pleasure to be here. I'll talk about 3D integration methods. This is largely work carried out at VTT, so there's a lot of VTTers listed here, but I'll also mention some contributions from Chalmers in particular. This presentation focuses really on these 3D integration methods. In particular, I'll focus on the through-silicon vias. That's the main topic. And then I'll say a few words about flip-chip bonding. And these alone, of course, don't make full quantum computers, but we're really lucky to collaborate with great partners. We have where we basically contribute these technologies. So we have this 50-qubit quantum computer build project at VTT carried out together with IQM. And then we also had a great collaboration with several partners in this Open SuperQ project that just recently finished. And in particular, with Chalmers, we had a close collaboration where there's work in progress on this 25-qubit QPU. But really, I'll focus on these. Let me say a few words about why I think this is really a really important topic, even though it's all fabrication, no equations here in this presentation. But why should we care about this 3D integration? Well, the field has made amazing progress in coherence times. They've increased from tens of nanoseconds to closer to millisecond. So that's 4 orders of magnitude. That's really impressive. But really, the fabrication has stayed very minimalistic, maybe even more minimalistic than some of the early attempts, maybe with the exception of air bridges, which have become relatively commonplace, and you saw on many of the slides in the previous talk. But I think it's very clear that we need to go to much larger processors, whether or not really smart people figure out some NISQ applications. In any case, I think that will not remove the desire to go to larger processors. But to go to larger processors, you just have to have basically more room for wiring, at least. And this is just not really possible with this minimalistic layer stack. And then the huge challenge, in my opinion, is to maintain this 4 order of magnitude increase in the coherence times while making the fabrication like an order of magnitude more involved, like in the number of steps and the kinds of steps that are required. Okay, so that's why I think this is really interesting and really challenging topic. But let me start. So let me start by saying a few words about the first step in this direction, which are these flip chip modules, and these have, of course, been done also in other places. But here's just to highlight that we've also done it, and it works pretty well. So this was collaboration in this Open SuperQ project in particular, where at Chalmers they made basically the qubit chips, and then at VTT we did the flip chip bonding part. And we don't measure DC resistance, so that's the good news. And then we bonded quite a lot of these modules and got some reasonable statistics and actually a pretty good chip tilt around 0.1 milliradian only, which is an important technical parameter that I won't go into right now. But basically the sort of great news here was that then at Chalmers, when they tested these qubits in these modules, they saw T1s that were very similar to what they measure in planar devices. So basically, the conclusion is that that doing the flip chipping process and the indium bumps doesn't mess up, doesn't cause disasters. So that's the first goal. And yeah, there's also work in progress to make this 25 qubit QPU with this flip chip geometry. And yeah, I would actually acknowledge also some contributions from ETH Zurich to this work. Okay, but I'll jump to the main topic that we've worked very hard on for a couple of years now, or even more, which are these through silicon vias. So first of all, why do you need through silicon vias? Well, one kind of obvious reason is vertical signal routing. So you could do something kind of trivial, just use the two sides of the chip for some transmission lines, or then like we saw in the previous talk, if you want to have an interposer and more than two chips, then it becomes basically essential to be able to route signals also vertically through the chip. So that's kind of the more obvious maybe reason. And then there's a slightly less obvious reason if you haven't looked into the details of this topic, which is that if you want to make larger QPUs by just increasing the size of the chip instead of making your qubits physically smaller, then you run into this problem of these parasitic microwave modes appearing in the chip. So here's an example where if you have a 30 millimeter by 30 millimeter square chip, if it's metallized on all sides, then, well, from a textbook, you can look up the formulas and you find that there's a resonant mode inside this silicon volume at 2 gigahertz. Then but you can basically control these with TSVs by just stitching the ground planes together. This is what's done basically in regular microwave PCBs all the time. And then you can push up the mode frequency to 12 gigahertz if you put TSVs that are spaced by 2 millimeter. And then if you add even more TSVs, you can push it further up. So here's an example where it goes up to 19 gigahertz. So that's why do TSVs, and then here's what we actually have done so far. So we've done a huge number of resonator internal quality factor measurements. And why do we do that? Well, it's the usual reason that we think it's a good proxy for predicting qubit relaxation rates, assuming that you make your transmon shunt capacitor with the same technology as you use for the resonators. And the geometry is the usual that I think many of you are familiar with, that we have a feed line, we measure the transmission through it, and then we have these coplanar waveguides coupled to it, and they each look like a bandpass filter at their resonant frequency, and then you can extract the internal quality factor and therefore the loss that you would expect in this capacitor. So in this image you see the waveguide or the resonator, and then these green circles are the TSVs, and these are now doing this via stitching of connecting the grounds on the front and back sides of the chip. Then we've done some experiments taking this kind of one step further, where you have also TSVs terminating the resonator, and then you can of course then do also non-resonant structures, which are sort of much easier from the point of view of loss requirements, but then require patterning of the backside of the chip. So just fabrication-wise, a little bit more involved. So what do our TSVs actually look like? We have this kind of well, the core part is this, and okay, here's many images of the same thing, because it's maybe a bit confusing. So we have this electrode layer that's tantalum, a tantalum film with a thin nitride film below it. And that's this orange part here. That's where we pattern the resonator, and that's kind of the sort of electrically critical layer. Then on the side walls of the TSV and also the back side of the chip, we have this ALD-grown nitride layer. And that's also important, of course, for electrically. And then in addition to that, we have this green colored layer here, which is a 2 micron thick titanium nitride membrane. And that's basically just a kind of mechanical, that's there for mechanical reasons. So our vias are hollow, so this keeps our wafer from being full of holes, which makes it much easier for processing than these wafers. But anyhow, we chose this structure because this has no deposited amorphous dielectrics. It only has superconducting metals, vacuum, and then this bulk silicon. And well, of course, at the interfaces, you'll have some non-idealities. These are pretty big, 60 micron wide, but the aspect ratio is 8, which is pretty similar to other solutions in the literature. And yeah, that could be worked on, but it hasn't really been our priority for the moment. Okay, so then what did we actually get? So I'll spend some time on this slide. So on the left, you see the different geometries of the chips we measured. And then in the middle, you see this typical internal quality factor versus photon number plots. And this is just a few examples because we measured like hundreds of these. And then it gets a bit too involved to analyze this. So we just focus here in the most interesting region for the moment, which is the single photon regime. So we can then make histograms of this internal quality factor value for the different kinds of samples. And then that's what you see here on the right are these histograms. And I'll start explaining them from the least interesting. So at the bottom, you have a planar niobium reference sample. So no 3D integration, just niobium resonators. And you see these Q values in a little bit above 1 million, which is typical. I mean, this depends on geometrical details, etc. But for this geometry, this is typical. Then the second from the bottom is a planar reference sample, but with the same electrode layer as the TSV sample. So no TSVs, but the same electrode layer, and you see a very similar performance. And then the top two ones are the ones with these TSVs stitching the grounds. And the difference is that the top one corresponds to this more sparse distribution of TSVs, and the second one corresponds to this more dense distribution. So basically, the great news here is that the kind of the typical performance for the resonators here is very similar to the niobium ones and in excess of 1 million. And I think this is basically as good as it gets with these planar resonators on silicon without any 3D integration, unless you then go to do some tricks to deal with the silicon native oxide. And furthermore, I think this is better than anybody else has published with TSVs on the same chip, as far as I know, and as far as is public. But okay, so that's really the result we're very proud of. But then if you start looking into the details, you can find some problems. So obviously there's like a few outliers here that have very low Qs, maybe more than in the reference samples. Also, the dense Q factors are maybe slightly lower than the sparse ones. Furthermore, if we then actually look at the resonators that have these terminations at the ends of the resonators, so the TSVs participate way more strongly in the mode, then we see much lower Q values, and also they become highly nonlinear. So already at thousands or tens of thousands of photons, the response becomes so asymmetric that we can't fit the basic linear response model anymore. So we don't have data points here. Furthermore, we have then low measured, very low critical currents for these particular chips in question, or these wafers, and like of the order of 10 microamps, which is only like a few kiloamps per centimeter squared of critical current density. So that these are not so ideal things about these particular samples. But anyhow, well, we reached these 1 million Qs with via stitching. So when they're not really carrying signals, so that's great. But then there's some evidence here that there is clearly limited signal carrying capability here. And our hypothesis at the moment is that these are our ALD process is basically not great, or the one we used here. And there's probably some kind of weak regions in the ALD film. Maybe it's different at the bottom of the via as it is at on the planar surface or something like that. And then, or another problem could be some contact issue here. But we think it's this ALD because basically we've done then separate tests, otherwise the same structure, but using a different ALD process. This time it was a thermal ALD process. And then we have managed to actually then see critical currents up to several milliamps, which is really what you want to have, because that would allow you to have, use this for flux lines, etc. And hopefully these outliers will then also go away. I'll just mention that we also have done these non-resonant structures, although due to a design blunder, there was actually a resonance there at some 7 or 9 gigahertz frequency. But this we think we understand and can fix. So maybe I'll just leave you with the conclusions, or how is the time? Is there time for questions? Yeah. So I'll leave you with the conclusions, and then there's some time for questions.
Thank you, Jonas. Indeed, we have time for at least one question. Maybe there in front.
Why do you use the tinitride below the tantalum layer? You said that you have a really thin layer of tinitride above the tantalum. Why you use that?
Yeah, that's right. So there's a few reasons. So one is that so tantalum doesn't grow in the right phase very easily on silicon directly. So tinitride is one way to induce this the alpha phase of the tantalum to grow. That's one reason. Then also it's easier to make contact to tinitride than many other materials. Doesn't grow a kind of a strong native oxide. Yeah.
Let's take a second one. Was there? Yep.
Great, thanks for the talk. So I was very curious about this nonlinear dependence you saw. Do you think that comes from the sort of kinetic inductance of the tinitride, or you have other ideas where that comes from?
Did you mean this one
yeah.
where I said that, well, we don't have data points because the response becomes nonlinear?
Yes, exactly.
Right, so I think this is basically just explained, because we also see very low critical currents, so, basically I think it's related to this that some of the TSVs are, they have low critical currents, so then when you ramp up the microwave power, you start to see the non-linearity of the TSV, like the currents already get to this microamp level through this termination via, and then it depends on this one individual via. So that's why I think also there's a lot of scatter in this data because the vias are not uniform apparently.
Okay, great, thanks.
Okay, time to thank Jonas once more. And the next speaker of the session is Mario Palma from IQM Quantum Computers. He's a quantum engineer there, and the title of his talk is Electroplated Indium Bumps for Scalable 3D Integration of Superconducting Qubits. So Mario, please.
Good morning, everyone. So I'm Mario Palma. I'm a quantum engineer in IQM, and I'm in the fabrication team. So I will give you an overview of our fabrication in IQM. And then further in my talk, I will talk about electroplating for scalable integration of superconductive qubit. So let's first see our roadmap for the QPU. So last year we delivered already the IQM5 with 5 qubit. It's already installed in VTT, and that's been done in collaboration with VTT. Now we are working on second generation, which is our IQM20. So we are going to 20 qubit. So that is now in the testing phase, and we hope to go for the 2023 to IQM54. So with the 54 qubit. But in order to achieve all this large number of qubit, we need to improve our fabrication and so in particular improve the qubit performance, the uniformity, and also our work on 3D integration to be able to scale up. So that's why in my talk, I'm going to talk first about the qubit fabrication, so some yield and also some junction uniformity. And then I'm going to go to the 3D integration part, where we talk about electroplated indium bump as alternative to the PVD kind of bump, and also the advantage of electroplated indium bump that give us the opportunity to achieve a really large chip-to-chip distance. So that is some of our kind of like single qubit device, and here we can highlight where we are with the T1 and the T2 echo. So that's some really high. That's some kind of some record value around 87 microseconds, and also T2 of 123 microseconds in line with the rest of the field. And then we can go on the uniformity. That's something that we were kind of like working. So try to make everything much more uniform. So having much more uniform critical current. This critical current has been extrapolated directly knowing the resistance of our junction at room temperature, and by knowing the superconducting gap of the aluminum. So in average, we get an IC around 30 nanoamp, and the variation is only a couple of nanoamp. So then we can go further in the analysis of this data, and go to a 2-inch wafer, where we fabricate this 624 junction, and we have basically 100% yield, so meaning we don't have any open, any short, and that's pretty good. And also we are really able to achieve our target frequency, which is around 4.5 gigahertz. So we can see that in average we reach this 4.5 gigahertz, and we have a standard deviation only of 100 megahertz. So give us 1 sigma deviation of only 2%, 2 or 3%. So the yield and the uniformity has been improved in the last years. So in conclusion, so we have improved the yield on the wafer scale. Also the frequency uniformity is much higher. Also we have really high control, so we can really get on target our qubit frequency. And also we have pretty good T1 and T2. Then going forward, so we want to scale up. So in order to scale up our QPU to go to large number of qubit, we need to develop 3D integration, in particular flip chip bonding technology. It's a really it's a really good technology that gives us the opportunity to go on the third dimension, but also in X and Y, as proposed by Rigetti with their chiplet concept. And also the further work will be on the superconducting through silicon vias that we are developing now in-house, and maybe in the future I can show some result. But here there are some results from the MIT, and also the results from the previous talk on superconductive silicon vias. So electroplated, so we decided to do indium bump, and usually indium bump are deposited by PVD technology. But at the moment, we decided to go with the electroplated indium. So for electroplated indium, it's kind of like a really good idea because indium it's pretty easy to electroplate with a really high efficiency, and also give us the opportunity, also as has been tested as a really good superconductor that give a really high quality factor in 3D cavity. In fact, in Yale, they were able to reach almost 80 million on electroplated indium cavity. And also, there have been some work on indium bumps, how to make it with a really small pitch, and really many of them. So the advantage to have electroplated indium is that we can really access a broad range of bump height. So we can go from a few micron up to 100 micron, and it is really easy to achieve this size. And also can be done in batch. So usually in the semiconductor industry, they use electroplating as a deposition technique. But the big challenge will be to see if this qubit, if our technique is qubit compatible, because this process is coming after the qubit layer. So the qubit has to be surviving this process. Then we can go forward, and so the flip chip technology, it's really a great, it's a good technology to scale up, but there are some problems. One of the problems is the tilt angle. In particular, if your tilt angle is above 200 microrad, might be quite a problem because we start to have some shift in the readout spectrum, and also we can have some frequency collision. One solution that has been already proposed by MIT was to use silicon spacer in the way to fix the distance between the upper tier and the lower tier. What we found out from our simulation is that another possible solution is to increase the chip-to-chip distance. That usually it's only few micron, but we are planning to go really high, something like 20 micron. In fact, in this regime, above 20 micron, we can see that the charging energy is not, of the transmon is not really changing with the change of the chip-to-chip distance. So if it is 20 micron or 22 micron or 25 micron, we will not be big effect. So the tilt angle will not be a killer for our readout scheme. So in fact, here there are some further simulation that we have done of a chip on the left, one with 8 micron distance, and we are assuming really big tilt, or consider tilt on the order of 200 millirad. And as we can see, for 8 micron, the readout spectrum can be really shift, and there is huge shift, and that can be a problem from the design point of view. While if we go to 20 micron, the shift is basically 0. We are applying still the same kind of tilt in all the spectrum, and basically there is not any big tilt, any big shift due to the tilt. So that's how we manufacturing. So I would say we start from the base layer with the qubit. So we have a first layer lithography, and then we have a seeding layer, which is important, that has to be continuous and conductive in order to be able to do electroplating. After that, we have a second layer of lithography, which is used to define our indium bump. And in the end, we electroplated and lift off both layer, and we end up just with our indium bump. So that's also what we started to do in the beginning. So in the beginning, we tried this kind of technology on a 30 by 30 millimeter tile, and we were first targeting something like 7 micron as a usual size for the bump. And so we were able to reach this 7 micron with, in average, something like 0.5 micron variation, mostly due to the grain size of our electroplated indium. And also we proved that this electroplated indium it is super conductive. And also, we were able to make some RF measurements. So in particular, we went to make some resonator where the indium bump was part of the resonator. And we can see that the quality factor is not largely degraded by the indium bump, but stays pretty much decent values around 600,000. So going forward, so we made also qubit. So we see if the qubit can survive all these additional process. And yes, they can survive, and we can get an average T1 around 45 microseconds, which is kind of like close to the average that we get usually. So going forward, so that's now how we make this really tall bump. That is the 20 micron bump. We still get pretty good uniformity. So in fact, we have plus minus 1 micron, mostly really due to the roughness of the top surface due to the grain boundary. And also, besides going to this really large dimension, also we don't have big effect on our tilt angle. In fact, we can reach still a pretty decent tilt angle, which are really similar to the 8 micron one that we usually use. So the tilt angle, they're going to be always below 200 microrad. So let's see if we can see some other performance. So then we went to test it, this kind of new design on a new test chip where we have 4 qubits, and they are all coupled between them. We went to check the crosstalk performance between the qubit and the driveline. And we have an increase on this crosstalk. The crosstalk is less, so it went from minus 20 dB to minus 40 dB, indicating that there is some good, our prediction on lower crosstalk was kind of like right. And also we have an increasing on the coupling between the qubit and the coupler that went from 60 megahertz to 90 megahertz. That also they were predicted due to the large chip-to-chip distance. And yeah, I'm already to my conclusion. So in the end, we proved that indium electroplated bump are a valid alternative to the indium bump deposited by physical vapor deposition. And also the fabrication process is Qubit-compatible. It's scalable on a large scale, on multiple wafer. Also, we have a large range of bump height that can be achieved, and they can give us a more relaxed design rule. And also, there are some advantages of this really large interchip distance. In fact, that can give a possibility to tilt possible problem due to the tilt angle, and also we can improve the parasitic crosstalk between the driveline and the qubit. And this work has been done between all the different teams in IQM, in particular fabrication, design, and cryogenic measurement, and also special thanks to the supervision of Asel and Kwan. And also, I would like to thank also the Excel Joint Undertaking Business Finland through the project QT and MatQ. And if you have any question, I'm here to answer.
Thank you, Mario, for the great talk. Will had his first hand up.
Yeah, thanks for the interesting talk. I just had a quick technical question. I think on your chart you said that the bumps were 8 microns and the chip-to-chip separation was 8 microns. Does that mean that there's no compression when you flip chip?
It's 8 micron on the that's just the dimension on the bottom chip, but it's also 8 micron on the top chip. The compression ratio it's 0.5 usually.
So both sides have bumps.
Oh, yes, yeah.
There, Graham. Far back.
Yes, thank you very much for the interesting talk. I have a question related to the spacing. So as you increase the chip-to-chip separation, you get lower crosstalk, but this also makes it harder to actually engineer coupling between the two chips. So do you know how you will address this with the increased spacing?
Yeah, it is already been optimized, the coupling. So that is mostly on the design side, this part has been engineered. But yeah, I think there will be not big problem. We already have engineered the coupling for this big distance. We are going to test also in a different multi-qubit QPU. So, sorry.
Then Sandoko.
Hi Mario, very nice result actually. So can I ask about this electroplating? So you actually have a seed layers between your bottom and top. So how thick is that seed layer?
The seed layer, it's usually around 100 nanometer.
Are you concerned about that your, I mean, if you use your bump for interconnection, for instance, like this might be an issue because is it resistive or?
Yeah, I mean it's a resistive base layer, but with the total proximity.
Okay.
Otherwise, I think we will not get this good quality factor. Maybe have also.
But that would be a different thing, I think. But unless you put your bump close to your resonator, I don't think you'll be able to.
I mean the bump are inside the resonator.
The bump is inside the resonator.
It's inside the central conductor of the resonator. It's in line.
Okay, that's very nice. Thank you.
Yeah.
Okay, let's thank Mario once more. And the final speaker of this session, Anton Potocnik. He's a senior researcher at imec in Belgium, and his title is High-coherence Foundry-compatible Superconducting Qubit Platform. So, Anton, please.
Thank you very much. Does this work? All right. Okay. So, yeah, hello, everyone. I come from imec. imec is a microelectronics research center, which is pushing the boundaries of microelectronics, going to smaller and smaller transistor sizes. But around 4 years ago, they decided to also want to go into the quantum computing business and try to fabricate some qubits. So we do both spin qubits and superconducting qubits, and I'll talk about how we would like to make superconducting qubits in this really nice building that you can see. This is our 300 millimeter industrial grade clean room. The work that I'll present is, of course, work of many people, but I would like to highlight Jeroen Verjouw and Rohit Acharya. So Rohit is here. We'll give a talk also later today. So these guys did most of the measurements and hard work. I would like to start with this graph. I think it's well known and a lot of people know what it's supposed to represent. But to me, this graph tells something else. It tells me that all of the state-of-the-art qubits from the last 2 decades have been fabricated with shadow evaporation and lift-off techniques. And there is a very good reason for that. Shadow evaporation can give you a very clean tunnel barrier, which is very important. But on the other hand, it will compromise on uniformity, especially when you want to scale to larger and larger wafers. And for us, practically, there is no 300 millimeter double angle evaporator available. So that's one of the issues. And of course, you are a bit limited in the materials that you want to choose for your junctions. On the other hand, lift-off technique is also very popular, common. And it's also an excellent technique because it protects you against, so it protects sidewalls, substrates, and other interfaces against various processing steps if you do them, if you need to do them. But again, there can be residues, metallic resist residues, which again is not favorable, is something that we don't want. And typically it's not compatible with 300 millimeter clean room facilities. So why do we want to make superconducting qubits in semiconductor foundry facility? There are some obvious reasons. So high uniformity. We know that we can make transistors really small with very high uniformity. So we hope that we can also make qubits, especially Josephson junctions with high uniformity, high yield, high volume. Maybe we don't talk about volume just yet, but we have to collect statistics. We know that our T1 times Q factors are quite broadly distributed, so we have to collect some statistics. So getting a lot of samples that we can measure is always beneficial. And of course, it's compatible with 3D integration. At imec and also other state-of-the-art facilities, we can process full 300 millimeter wafers. I would like to stress that these are silicon wafers. There are no, at least to my knowledge, no sapphire 300 millimeter wafers. And then we can use advanced lithography techniques like DPUV, immersion lithography, extreme EUV. So, for example, we use DPUV. EUV is a bit too expensive also for us. But then, in general, we do sputtering deposition on the whole wafer, and also the processing of wafers is done by the processing like etch, strip, and clean are all plasma-based for very good reasons. But when thinking how to fabricate superconducting qubits, this might be a challenge. Well, so shadow evaporation is not compatible with 300 millimeter cleanroom tools. And the question is, are there Josephson junction fabrication techniques that are compatible? And the answer is yes. And there are tri-layer Josephson junctions that have very rich history because tri-layer, mostly niobium-based, have been used for many other applications like squid sensors, SFQs, parametric amplifiers. So Will Oliver has done quite a lot of work in this direction. But in general, they give relatively low coherence times compared to shadow evaporated Josephson junctions. And the reason is I think rather straightforward, is that the process is rather complex. There are many steps, there are many interfaces, many problems that can occur, and you have to deal with that. Fortunately, there is an alternative approach, so-called overlap Josephson junctions approach, that is a bit simpler. And I think the first work was done by Martinez, but please correct me if I'm wrong, if there was some earlier work. But in general, the revival more or less happened in 2015, 2017 with the work of David Papas and Ian Popp and Martin Weides, where they start showing reasonable coherence times on contemporary qubits. But which is super, super nice. And for us, it's very inspiring because it seems that this is the method we could then modify to make it fully fab compatible. So unfortunately, the processing that they showed is not fully fab compatible. It's very close, but not fully. So the answer, what we are interested in, whether we can slightly modify this process and make it really fully fab compatible, that we can then one day fabricate these qubits in a large 300 millimeter cleanroom. I'd like to emphasize that the work I'll present was still done on a smaller coupons in a lab environment, simply because the turnaround time is much faster than in the fab environment. So I'll distinguish between lab and fab. So fab is a 300 millimeter fabrication processing. Okay, so how the overlap junctions are made. So we start with silicon, high resistivity silicon substrates, either 3 kilo centimeter wafers or coupons that are cut from large 300 millimeter wafers. Unfortunately, we cannot commercially get any high resistivity 300 millimeter wafers. And then we also use smaller wafers with 20 kilo centimeter resistivity. We perform surface clean with HF and then deposit aluminum very quickly after. In the next step, we pattern the bottom electrode of the Josephson junction using either wet etch or dry etch. And after strip, we get a bottom electrode. So what we do is we merge the bottom electrode and we call a resonator layer, which is everything else. So the resonators and the ground plane. And at this point, we had to break the vacuum. So half of the junction is fabricated, but we had to break the vacuum. So that means the surface is fully contaminated with native oxide and everything else that is in the air. So in order to make a Josephson junction, we evacuate this in a deposition tool. And first, we have to get rid of the native oxide. And that we do with argon milling step. That's the most critical step, which can introduce defects on our surfaces. After the argon milling step, we do controlled oxidation, and then immediately in vacuum in situ, we deposit the top electrode everywhere on the entire chip or coupon. And after that, we do top electrode patterning and etching. We do a slight over etch. I'll talk about this later. And in this way, we get a Josephson junction and a straight Josephson junction. And from the top, you can see the bottom electrode of the Josephson junction is connected to the rest of the structure, and then we have a small part of the top electrode with a junction and a straight junction. So our guiding lines are very simple. We wanted to make a simple process with as little fabrication steps as possible, that will give us as little interfaces as possible. So we only use aluminum. We merge bottom electrode and resonator layer, and we do a slight TE over etch for a reason to remove any defects on the outer surfaces introduced by the argon milling. All right, so this is the overlap approach. It's different than shadow evaporation, but is compatible with what we can do in a large cleanroom environment. Of course, now we are interested in what kind of coherence times we can get with such an approach. Mostly, personally, I'm interested what are losses inside the Josephson junctions, because inside the Josephson junctions, there are defects introduced by the argon milling. So in order to answer this question, we fabricate qubits. We will use fixed frequency transmon qubits with Princeton design with more or less standard parameters. Perhaps EC is a bit shorter. And then if we zoom in, the overlap Josephson junction looks like this. And if we do a cut, you can see here on this cartoon what we expect with all the interfaces. This is the cross STM. So we see a bottom electrode, aluminum, a top electrode, also in aluminum, and then a barrier here in between, and a substrate and some dark regions, which we'll talk about later. Okay, so if we look at the coherence times, these are the results. So these are T1 measurements as a function of time. So we repeated these measurements over a span of several hours. And we were very surprised because these were the highest values we've measured ever in our lab. So that's very encouraging. So the mean values are around 60 to 70 microseconds, with the highest values go up to 100 microseconds. And then the mean values also in T2 star and T2 echo are around 60 microseconds. So we are very happy about that. And then we also perform a randomized benchmark and extract single qubit gate fidelities of 99.94. I'd like to point out that this is still not incoherence limited. So the big question is, if we make our approach fully fab compatible, that means we use dry etch, subtractive dry etch, and limit ourselves to 300 millimeter wafer resistivities, which is 3 kilo ohm centimeter, are we losing in performance in coherence times? Would something that is a bit more lab-like, something that people use and have been reporting in literature for quite some time, would that yield better results? So for example, if we would use higher resistivity wafers or, for example, wet etch. And in order to answer this question, we fabricated a number of devices and compared T1 times. So here I show a violin plot, which essentially represent a distribution of T1 time measured over a span of several hours for differently processed wafers. So here on the left, we have wet etch with 20 kilo ohm centimeter wafers. It's something that we would think hits closer to lab conditions. And on the right side, we have dry etched 3 kilo ohm centimeter wafers. And what we can see is that there is no qualitative difference between these devices, which is extremely encouraging for us and tells us that if we transfer this process to the fab environment, we don't expect to get lower performance. All right. Next, we wanted to know how much loss we have inside the Josephson junction, and on the other hand, what is limiting the performance of our qubits. In order to answer this, we fabricated a number of different sized qubits from this transmon, like a double pad transmon to an XMON, all the way to a high-Q resonator, which is on every chip. And we performed TCAT electrostatic simulations to extract surface participation ratios. And after we measured all the T1 times of these devices, we plot 1/Q to renormalize with frequency as a function of, for example, metal-air surface participation ratio. And if we limit ourselves only to qubit data, the data nicely lines on a linear, on a line, which indicates that the losses do scale with the surface participation ratio. I forgot to mention that all the Josephson junctions are designed more or less the same. So the only thing that really changes is the size of the capacitor. So this directly tells us that most of our devices are limited by the surface losses of the capacitor and not by the Josephson junction. This is further supported by the fact that the line intercepts also the data of high-Q resonators, which don't have Josephson junctions, so the loss scales there as well. And then we can have a look at the offset in the y-axis. right? So this will tell us what are the losses that are associated with the Josephson junction and Josephson junction's environment or surrounding in the limit of, let's say, the capacitor is infinitely large. And that offset is around 130 microseconds, with T1 130 microseconds for 3 gigahertz qubits. And that could set a limit on the losses inside the barrier, but it actually turns out that in our experimental setup, there are also other sources of loss, like quasi-particle tunneling, possibly box modes, stray junction is still there, and of course, surface losses around the Josephson junction, in addition to the losses inside the barrier, which we are really interested in. Why we are interested in that is because it's really difficult to clean any defects inside the barrier, inside the junction, and all other contributions we can and we are trying to eliminate at the moment by improving the designs, improving the experimental setup, and so on. Okay, but anyway, what we can conclude is that this 130 microseconds seems to be the lower limit of T1 times limit by the barrier, which is very, very encouraging because it's close to the state of the art. What we can also look at is morphological results. So morphologically, can we see where defects could potentially be? So what argon milling is doing and what are the consequences of a subtractive dry edge? So first we can focus on the junction area and perform scanning tunneling electron microscopy. And you can see results here. So this is the barrier, and if we zoom in to this corner, we see a bottom electrode and the top electrode, around 2 nanometer thick oxide barrier. So the first thing we notice is that we don't see any visual structural defect in aluminum because this surface here saw heavy argon milling before controlled oxidation. So that's very, very promising. On the other hand, if we have a look at the EDS, which is energy dispersion spectroscopy, we see that we have oxygen, of course, in the barrier. We have a native oxide on top, but we also have slight residues of silicon and argon inside the barrier. This is potentially going to be a problem, but so far we don't seem, at least to 130 microseconds, we don't seem to be limited by those losses. Okay, so that's that interface. And if we look at the silicon top electrode interface, we immediately see that below the top electrode there is a gray area. If we look at the argon signal, it's there. So this gray area actually turns out to be the amorphous silicon induced by the heavy argon milling. And it's roughly 5.5 nanometers thick, which is known to contribute to loss. That has been reported before. But the good thing is that this area stops just below the top electrode. So if you look at the exposed silicon areas, there is no argon. And this is a consequence of slight top electrode overedge, which removed all the defects induced by the argon milling on the structure that is everywhere else except on the top electrode. And that's why we want to do this top electrode as small as possible. Okay, so that's the top electrode. And there is another potentially problematic part, and this we call it the silicon crust that forms around the top electrode, and this is simply because our subtractive dry edge is not yet fully optimized. So we have hard times removing this, but we are also working on that. Again, limited only to a small part of the Josephson junction where the top electrode is. And then finally, the substrate bottom electrode interface, which represents the large part of the qubit. We see a very clean interface between silicon and aluminum, around 1 nanometer thick. And this is very, there's practically no oxide here if you look at the oxygen line. On the other hand, we again confirm what we saw before, that the silicon part contains no argon, which means, again, that the substrate has been cleaned. But what we think is the main source of loss in our case are these sidewall residues that are rich in silicon oxide and also aluminum. And that we see, for example, also in this picture here, and I try to illustrate on the cartoon. So we think that this is the main cause of loss in our devices. And with that, I would like to conclude. So we managed to show that the overlap Josephson junction qubits can have reasonable and nice coherence times, and that losses are still limited by the capacitor, which is great news because it's much easier to clean the outer surfaces than the barrier. And the barriers so far seem to be limited down to 100 microsecond. So the next steps is, of course, we are transferring this process now to the 300 millimeter clean room. It does take some time, but so far, so good. And of course, we are trying to come up with better cleaning methods for outer surface and trying to better zoom in into what are the real losses inside our barrier. And that has been recently published in MPJ Quantum Information. So if you want to check details, you can check them there. Thank you very much.
Thank you, Anton, for the interesting talk. And let's have one question. Will?
Yeah, thanks a lot. That was really great talk. I was curious about the curvature of the bottom electrode and how you did that both in your lab and then how you would plan to do it in your fab.
Right. So the profile of bottom electrode is, I would maybe say, a slight unfortunate consequence of a combination of a dry etch and argon milling and some potential residues that happen. So this is not something that is intended. So in the fab where the tools are better, we expect that to be much sharper. But we also have a possibility to smoothen it out to make the corners less sharp. So, but that's a second order problem.
Can take a quick one there, Alessandro.
Yeah, thank you for the excellent talk. Can you comment whether these samples, and in particular the one with the crust, is, for instance, cleaned with solvents or with final oxygen plasma, I guess? I mean, is it the lab or the fab approach?
So what I showed here is all lab approach. And yes, we have tried to clean with solvents and other cleaning in the paper is described. And we also do oxygen ash at the end. So we tried all the basic cleaning steps, but these are not enough. So we are exploring some more alternative cleaning steps now.
Okay. So I'm encouraged to continue the discussion during the coffee break. And now I would like to ask you to thank you, Anton, and all the speakers of this fab session.
So we will continue here in 20 minutes. Enjoy the coffee break together with Keysight, and see you in a bit. Hey, Rohit. So the next session is about to start. So I'm happily giving the microphone to Christian Kraglund Andersen from TU Delft to chair the session. Thank you, Christian.
Great. Hello? Okay, yes, perfect. Okay, great. Thanks for the introduction and thanks for allowing me to be the chair of this session. So my name is Christian Andersen from TU Delft QTech, and I'll be chairing this session on gates, readout, and reset. And the first talk is by David McKay from IBM. He will talk about reducing errors using superconducting qubits and algorithms. So I think that's perfect for the Superconducting Qubit and Algorithms conference. So go ahead.
All right. Okay, thank you. All right, let's get started with this session. Let's move this a bit. Yes, so I'll be talking about reducing errors via device and algorithmic improvements. So I'll be talking about high fidelity. So I think it's fitting for the session and gates, but I'm also going to throw in a little bit of about algorithms as well. So I think that, as Christian mentioned, fits in well with the title of the conference. So just a motivation slide why are we all here? That's to produce noise-free outputs for problems of interest with quantum computers. But we've heard quite a number of times that we're in this so-called NISQ era, so we are dealing with noise. But ideally, we can produce a circuit like this, and we evolve with gates that are perfect unitary matrices. So what are gates? Okay, very high-level description here. Gates, we take our device, which in this case is a superconducting circuit. It's described by some Hamiltonian, but it might also have some decoherence terms as well. We apply a set of control tones with a rack of control electronics. We've seen some nice examples from some of the vendors. And we use software to design the shapes of the pulses, and hopefully what comes out at the end is an ideal gate, which is, again, an ideal unitary matrix. That matrix might also have some unitary terms that we did not intend to have. That'll be like a coherent error, but it may also have some incoherent errors, and those are going to be represented in general by a quantum channel error map. We saw that kind of nicely in the talk by Amy yesterday. So what I'm going to talk about today is reducing those errors both with device level improvements, so things like improving coherence, reducing control errors, and in improving our coupling, but also with algorithmic improvements. So yesterday we saw Andreev's really nice talk on quantum error correction. That's one methodology for improving device errors with an algorithm. But I'm going to talk mainly about error mitigation, which is kind of more of a near-term methodology for reducing errors. And in all of these approaches, both quantum error correction and error mitigation, there's a real tie-in to device-level improvements because any algorithmic overhead is greatly improved by device improvements. So here's kind of just a quick slide on error correction. I don't have to go over it in detail because of the nice talk yesterday. This is our code, the heavy hex code. But the main takeaway from this slide I want is that once we're below threshold for the code, what we can do is reduce errors arbitrarily by trading off against the number of qubits. So quantum error correction is really a space trade-off for errors. Another way of reducing errors is to kind of better understand our devices. If they are coherent errors, we can do things like optimal control and dynamic decoupling. This is nice. There's no real trade-off except understanding and maybe complexity of the circuit, but there's no space or time trade-off. So if we can do dynamic decoupling, we absolutely should. But the third method I want to talk about is error mitigation, which is kind of a more continuous path from today with our NISC devices to where we can get with error correction once we're well in the below threshold regime. The trade-off is that error mitigation has an exponential cost. So there's no free lunch there, but what we're hoping is that the exponential cost is scales better than the classical exponential cost that we're trying to compete against. In the past few years, we've seen, at IBM at least, we've pushed error mitigation with this extrapolation technique, but what I'm going to tell you about today is a more recent result on using probabilistic methods to do error cancellation. And here, unlike the space trade-off that we made with quantum error correction, we're going to make a time trade-off. So we are going to have to do an exponential number of circuit runs. But again, hopefully that scaling is not so severe. And what we'll see is that the scaling depends very strongly on gates and the gate errors. So this is a nice motivation and a good metric for how to improve gate errors. And it's what we think is a path to quantum advantage. And there's a very, nice formula here for the runtime of this error mitigation technique. I'd like to focus on this gamma parameter, which is a benchmark of the noise in the device. I'll explain it a bit more later, but that's the exponential parameter. So if you have a circuit with n qubits and depth d, it's going to scale like gamma to the power of n times d. And if you're doing a large circuit, say you want 100 qubits, 100 depth, 100 times 100 is a big term in that exponent. So this gamma has to be very low. And if you have an error-free circuit, gamma is going to be 1. So the method is probabilistic error correction, error cancellation. And the idea is that if we understand our noise model, we can apply the inverse error channel and just cancel it. Of course, that's easier said than done, and it's not a physical operation that we can apply to the chip, but we can do it in a quasi probabilistic method by running a number of circuits with randomly injected poly terms based on our understanding of the map, and then sum back to an error-free value. But again, as I mentioned, the trade-off is in time. We have to run many more circuits. And this is kind of a cartoon of what I was trying to say with the scaling. Classical circuit running for quantum algorithms is scales exponentially. That's why we're here. Quantum error correction shouldn't scale exponentially. Maybe some polynomial cost here, but it has a high overhead cost initially. And the idea that we're hoping is that with the quantum error mitigation techniques, we can start to fall below that classical line for some complexity, but eventually we'll have to meet back up with quantum error correction. And this kind of table is some calculations of some of that scaling for classical versus quantum for this method, and where we think that gamma parameter has to be competitive. So very, very close to 1, but you'll see some numbers from our current set of devices, and we're kind of getting into this regime. So here's a toy model of the technique. Let's say you have bit flip noise, and I've kind of co-opted this from a nice talk that Zlatko Miniev gave on our QuizKit YouTube channel. So I do recommend you watch that if you have an hour. But if we have a bit flip error model or error channel, there's some probability that we don't flip, and there's some probability that we do flip, which is going to be an X poly operator. And so the error channel is given at the bottom here. We could write an inverse of that error channel, but it's not something that we could do physically on the device. But you can, say, run the circuit as you normally would with that error channel, and then run it again where we've on purpose applied an X poly operator. And then we're going to get 2 outputs of the device, and we can sum them in the right way. Here's this Q parameter that is going to be negative. We can sum mitigated observable with the right scalings and prefactors based on the error channel that we had, and we will get an error-free mitigated observable, but the scaling is going to be quite severe depending on how high the errors are. Okay, in the a real-world implementation, we have a much more complicated map. So we first polytwirl each layer of the device to learn the map and simplify the map, because then it'll be diagonal. And I'm basing this on this paper that was out earlier this year, which has a lot more detail. So, please check out the paper if, because I'm giving a very shallow overview of the entire paper. So we learn the error map with poly benchmarking, assuming a sparse model. So only we're cutting off at weight 2 polys based on the connectivity of the device. Then we do this error mitigation technique, this probabilistic error mitigation technique. This slide is exactly the same. I made a mistake. Here are some of the outcomes from this paper. Again, I implore you to check out the paper for more details. But for a 10-qubit demonstration of an Ising model, a trotterized Ising model, you can see the difference in observables without error correction, and then error cancellation, and with the error cancellation. And then at a larger circuit, but a kind of very simple circuit example, just applying C0 gates on 50 qubits. So it should be equal to the identity gate, because it's 2 layers of C0 gates applied across these 50 qubits. Without, if you want to go up to the weight 49 observable here, you can see that even for 2 layers on a pretty one of our state-of-the-art devices, you almost get down to 0 at such a high weight because of the level of errors currently, but then with the cancellation technique, you can recover mostly what you expect. And again, it's this battle of exponentials here that is a trade-off between the quality and the number of circuits that you have to run. Speed is also a critical element if you want to compare to actual wall clock time. Because we're starting to get into the level of circuits where it may require running for an entire day or even longer. So the difference between repetition times is now pretty important in terms of how long it will take to run. And then, as I mentioned, here are some measurements of this gamma parameter on our devices, and looking at kind of improvements in device evolution. We are starting to see this number get down lower and lower and closer to 1. Still, I think we need to go a bit further. As I mentioned on that first slide, this has to be down to 1.001 to do this 100 by 100 qubit example, or circuit example, sorry. Okay, so one of the other metrics for device quality that we push a lot is quantum volume. And we've steadily shown how that improves over the years as we've increased device quality. And there should be a pretty good relationship between quantum volume and gamma, and this device with the best gamma is also the device with the best quantum volume. And here are the error rates on that our Prague device down at the 0.1% 2-qubit gate errors, which is, I think, quite exciting. And one of the improvements on, I'm not going to talk in depth about the improvements that have led to that, but they have been due to improvements in coherence. You can see kind of evolution between some of our earlier Falcon devices, which are our 27-qubit device, revision 5 versus revision 8. The T1s, here's 100 microseconds. So those have moved up to kind of in the few hundreds of microsecond regime. And then on some test devices, we're starting to see kind of 1 millisecond type times. And then, and that's kind of corresponded as well to some steadily decreasing 2-qubit error rates, and down now to Prague, which is in the 0.1% kind of neighborhood. Okay, so in the final part of the talk, I think I have maybe about 5 more minutes. I want to mention how we've, 5 minutes exactly, thank you. How we can kind of link these two techniques. As I said, this gamma parameter is very linked to the quality of the gates that we're doing, and how we were removing unwanted terms from our gates. And so in the last little bit, I want to talk about this technique that we developed for removing ZZ terms using microwave tones. So we're all kind of familiar with this canonical setup that we have in these superconducting systems. We have two transmons. They're coupled by maybe a direct coupler or a bus, but we can write that as a J-coupled system. And one of the main parasitic terms that we have, if we leave those qubits always coupled, is a ZZ term that is unwanted. We want that ZZ term to be 0, but if we have always on, it's this J coupling will leave us with some ZZ, and that will increase this gamma parameter. Last year or 2 years ago, we kind of fortuitously found, in parallel with some work at Berkeley, we fortuitously found that if you apply simultaneous Stark tones to qubits, so we're all fairly familiar, I think, with Stark tones. If we apply an off-resonant microwave tone to a qubit, it'll shift the frequency around. This is kind of a useful technique for a variety of reasons, but particularly if you don't have a flux knob in your system. But we found that if we apply it simultaneously to qubits and you control the relative phase, you can also control the ZZ interaction on top of the frequency of the qubits. And the expression for that is given here. You can see it depends on J, the power that you put into these Stark tones, and then interestingly for us, the phase. That was kind of a surprise to us. And in Vlad's Fluxonium talk, he also talked about ZZ with Stark, but there, because of the level structure, it's kind of nice. You can only use a single tone, but here with transmons, you need to use these two tones with phase stability between them. But what you can do with this kind of technique is you can take a really high coupled device with maybe has close to a megahertz static ZZ, and you can bring that down to 0 just with a CW cancellation tone. And that has a huge effect on something like simultaneous single qubit randomized benchmarking. Here, the blue is the high ZZ curve. It decays very quickly. But then when we cancel it, we get our kind of standard, decay over a few thousand Cliffords. We can do full device mitigation of ZZ. Here, this on a standard Falcon device, which has kind of typically 50 kilohertz ZZ. So the ZZ, again, is proportional to the power in the tone and the phase. So here we've done a cancellation across the whole device. Here's the a plot of all those ZZs, and you can kind of see bounded by a few kilohertz. We can turn it off and recover the kind of static ZZ that we'd have with the standard device. Again, kind of 50 to 100 kilohertz. We can, another kind of nice part of the technique is we can also double the ZZ, and you just flip the phase. So here, we add a pi to the phase, and then we get double the ZZ. And what we're going to in the final few slides, we can then measure that gamma parameter with and without dynamic decoupling, and show how this sizzle technique, which is this Stark ZZ technique that we developed, we can use that to inject noise and see how this gamma parameter changes with noise. It's also something I think we plan on doing for looking at our D=3 code. Okay, so just flashing our roadmap really quick. We also have it out on our booth if you want to stare longer at this slide. But I think we, with realistic reductions in the gate error, this 100 qubit by 100 layers with noise mitigated observables is close to reality. And I'll flash my conclusion slide really quick, but I think I'm running out of time. So thank you for listening, and I'll take, I think, a few questions.
Great, thank you to David. Let's take some questions. We have one down there.
Yes, wonderful talk. Really impressive to see the improvement in T1 times. My question is, have your T2 times kept up?
I'd say for the most part, yes, we're still seeing kind of this T1, approximately T2 regime, but yeah, nothing that has been notable to me in a reduction in T2. Yep.
Great.
I think for some of these devices, you can kind of map this online in Qiskit as well for the ones that have the high coherence.
Let's take one more. We have Morten.
Hi, David. Thanks for the wonderful talk. Cool to see all the developments. So the probabilistic error correction, you showed some, especially in the weight 49 or whatever that really impressive number was. The expectation value was greater than 1.
Right.
That's not how it usually works. How am I supposed to interpret that data?
So, I mean, there's going to be some, there's some bound on, how close you are to the expected observable. And I would, again, I'm probably push you to the paper for Ewout who did the theory for this to kind of give the definitive answer. But, there's going to be some bound on that because it is, you are taking, you're scaling and summing observables, so you can get things that are now non-physical if that sum is off, and there's some bound based on how many runs you have to do, and if everything's well behaved, it should converge to the right result. But I think there are a lot of interesting open questions in like how, time varying noise and things are going to affect this. Yes.
If there's a quick question, we'll take the last one.
Thank you very much for the very nice talk. You mentioned about the importance of this parameter gamma, which is the cost of probabilistic error cancellation. And you mentioned that it has something to do with the physical noise of the hardware. On the other hand, one can argue that it also depends. So basically, if one uses some other complete basis for quantum operations, one can also reduce this parameter. I was wondering if you have a systematic method how you choose what basis of operations you use for the probabilistic error cancellation.
So you actually measure gamma for each layer of gate operations that you're going to use in your algorithm. So gamma is also a property of the algorithm itself. And so this technique works particularly well for algorithms that have repeated layers like trotterized simulations. So I hope that answers your question. Yeah.
Let's thank the speaker again. And in the next talk, we will hear about readout of superconducting qubits using a nano bolometer. And this is from Gunoho from Aalto University.
Thank you.
And we're still waiting for some slides.
Okay.
There you have it. Perfect.
Okay.
Take it away, Andres.
Yes. So, hi, I'm Andras. I'm a PhD student at Mikko Möttönen's group. And this work was also, we got some help with the fabrication from people at IQM. And so I'm going to talk about readout using a bolometer. And so I'm going to quickly review dispersive readout and then explain to you how the bolometer works and then show you what we measured. So, okay, this is you basically all probably know how the dispersive readout works. You have a you have your qubit, you couple it to a resonator, and then you pass some microwave tone reflected off the resonator in this case, and then you measure what comes out. So, okay, physically, in our case, it looks like this. We have a feed line, and we have 6 individual qubits. So we just have many qubits on the chip, so we can test different things there. But when you look at the signal that gets reflected, then depending on the qubit state, the resonator will have a different resonance frequency. Normally, you would measure here between the frequencies and look at the phase of the signal. This is kind of the standard dispersive readout, but actually what we're going to do is measure here at one of the shifted resonance frequencies, because the bolometer actually only sees the amplitude, so we cannot use it for the phase detection. Okay, so what is the bolometer? So basically, bolometer means just any kind of radiation detector based on measuring a difference in temperature. So in our case, what we have is a normal metal nanowire, so gold palladium, and when some and we put aluminum, superconducting aluminum islands there, so we have like a bunch of SNS junctions. And when we get some radiation here from the H heater port, the temperature of the electrons in the nanowire like quickly saturates across the whole nanowire, and this will actually change the impedance of this chain of SNS junctions. And then we just put it as part of an LC circuit. So when you have this impedance in the LC circuit, and it changes as a function due to the electron temperature, the resonance frequency of the LC circuit changes, and then we probe it. So we reflect some microwaves of the circuit, and the resonance shifts depending on the whatever radiation you get in here. And here is just an example. So the probe frequency is typically hundreds, below 1 gigahertz. Yes, and then so this is the device I'm going to talk about here, but also we've recently kind of further developed this where we replaced the nanowire with a sheet of graphene. And that helps a lot because it has a lot smaller thermal capacity. So then it's much more sensitive. So much smaller number of photons coming in will heat it up more, basically. Okay, so and then just a couple of words of why would you want to use a bolometer instead of a parametric amplifier. So that's what we're going to do. So we take the output of the readout, and instead of putting it to a parametric amplifier, we're going to just plug it into the heater port of the bolometer. So with a parametric amplifier, you have a setup typically like this. You have your signal, and it goes through a couple of isolators, and then you have your pump, and then you get your amplified signal out. And here, okay, actually the arrows are in the wrong direction. But anyway, you need these isolators because you're pumping your tupa roughly at the signal frequency. Okay, it's not the same, but still it's close. So you want to isolate. You don't want your pump frequency to go back to disturb your readout. And also, as discussed in one of the talks before, the tupa can also amplify like vacuum fluctuations in the backwards direction. So that's also why you need the isolators. In comparison, because the bolometer is probed at like, actually in our case, like 600 megahertz, so it's very far away from the resonator, you can basically directly connect your output to the input port of the bolometer, and then you just use a reflection measurement with the directional coupler. Yeah, so this is what I also already mentioned. Oh, and then another thing that I don't have here is that the pump amplitude is actually way smaller. So the bolometer, so with the tupa you have something like a minus 100 dBm. With the bolometer is more like minus 140 or minus 160. So there's several orders of magnitude less power at the probe, which is also nice for when you want to scale up, when you have many of these devices. Okay, so this is the experimental setup. So on the left side, we have kind of the standard qubit. So we have AWG to excite the qubit. We have flux control. And then we have a microwave generator for the readout. And then actually, in this case, we have the isolator because we were not entirely sure if the bolometer is going to work. So we actually had to switch to also measure the qubit normally. And we have some extra components to try the bolometer also separately, but we're not going to do those, so we're just measuring using this green line. And then for the bolometer, you have your 600 megahertz probe, reflected off, and then heterodyne demodulation and digitization. OK, so first, before you do anything, you need to characterize your bolometer. So you want to find the resonance of this LC circuit. So you scan the amplitude and frequency of this probe tone, and this is what you get. And here's just a crosscut. You have some resonance. It looks kind of shallow, but the scale is a bit not so good here. You'll see in a moment why. But when you increase the probe power, what happens is that the resonance becomes a bit sharper. So that's good because you're going to look at how this resonance shifts. So if you have a higher gradient, then you have a better signal. But you don't want to go too far because then actually the signal from the probe itself is going to heat up the bolometer, and it's going to kind of cause feedback, and actually you will observe hysteresis in this. So you can actually use that to your advantage, but here we're not going to do that. OK, so then we put some pulse through the readout, and actually we don't care about the resonator yet. We just look at what how the bolometer signal transmission shifts when you input some pulse here. And here, actually the pulse is very long. It's 2 milliseconds, but we can clearly see the kind of voltage we measure from the bolometer, and we define the signal as take the part before the pulse and then take the end of the pulse and calculate the difference. That's the response. And then here we also map out how it varies with the bolometer frequency and power, and we get a map like this. So kind of broad range of frequencies. It's a nice signal. But actually, for readout, of course, 2 milliseconds is way too long. So here's the same with the 10 microsecond pulse. And here you can see that now it's a bit more important which frequencies you select for the bolometer. And OK, so then we pick an operating point here, and we chose it here because here at the higher powers, as I said, you get this feedback effect, which you'll see in this measurement even better because then the decay time. So here the decay time will not be diverges because of the feedback and so on. OK, so we pick this operating point, and from there on the bolometer, kind of we don't touch it. It's actually just continuously on. We send a pulse, and we look at the ADC as we put the pulse. So then we do kind of your standard qubit measurements. So here we do, quote, spectroscopy just with 10 microsecond pulses. And we measure what the bolometer sees, and we can see the resonance. So that's nice. Then we park our resonator tone and do qubit spectroscopy, and we can see the qubit also. So that's also really nice. And then we can, of course, do a Rabi measurement, sweep the qubit pulse length, and look at the response, and we can really see Rabi oscillation as well. And then also we measure the T1, and for this qubit, it's 28 microseconds. So it's kind of basic qubit, nothing special there. That's also, and OK, I forgot to mention, so these are actually on separate chips. So you really have a qubit resonator, a standard chip, as I showed in the picture, and the bolometer is just a separate chip and connect with the SMA cable. OK, so then the biggest question is, like, can you do single shots with this? And the answer is kind of. So here we tweak the probe, the readout pulse properties to get the best possible fidelity. So we need to increase the length actually up to 20 microseconds and the amplitude all the way up to until the resonator becomes nonlinear. And this is the kind of best we get. So when you calculate the fidelity from this, you get 0.49. So then, OK, so the readout is 20 microseconds. That's pretty long compared to the T1, which is 30. So we can ask, like, how much of this error is just because the qubit decays back to the ground state because of T1 decay? And that we do by fitting Gaussians. So this is the same data. We fit a sum of Gaussians, and let's assume that the T1 is infinite. So then we just look at the kind of ideal Gaussians we would have, and from that overlap we get the fidelity of 0.9. So yeah, that's basically my results. So we were able to observe a qubit through this bolometer, and with this setup we get a fidelity of 0.49. And then there's a couple of things you can do to further improve this. OK, you could tweak the qubit and the resonator kind of change the chi over kappa ratio and things like this. And then you can do tricks with the readout. So here we just we did the dumbest thing possible. We just put a pulse. But you could use this feedback of the bolometer to your advantage, or you could drive the resonator with some special pulses with high power and so on. And then you could do some extra filtering on the data, which is also what we didn't really do here. But the biggest thing to improve this would be to change to this graphene bolometer, which we've had some fabrication problems with. But with the graphene bolometer, you can, so here from this plot, you can see that the decay constant of the bolometer is on the order of hundreds of microseconds. And with the graphene, it goes down to hundreds of nanoseconds. So with the graphene bolometer, you could really do single-shot readout in a short time. And that's the end of my talk. And this is our group, and these are our supporters. Thank you.
Great. Let's start with Christian here.
Hello, and thank you for your nice talk. I did not follow why you needed such a long readout pulse of 20 microseconds, especially when your T1 was like 30. I mean, that's a really long pulse then.
Yes, so the reason is that the bolometer has a time constant of 100 microseconds. So if you think, actually the rise time of this pulse would be the same as this decay time you see here. So if you would continue this, if you would have a long pulse, then it would have it would go like all the way up. So you would have a huge signal, but it takes like milliseconds to get there. So I did kind of as a short pulse as possible. Well, basically I checked which pulse gives the best fidelity, and above 20 microseconds, the qubit decays so much then it doesn't improve.
Great. Then take question.
Thank you for your talk. There was a detail that I maybe missed, but you showed clearly the response, but not what kind of input signal you're giving there. Because I'm assuming there's some kind of gain in the signal, but I couldn't find what you put in there.
What do you mean by gain?
Well, I'm assuming that you're posing this as a replacement for a typical parametric amplifier. You're showing how it responds, but I'm assuming that...
yeah, okay, so what kind of amplitude is going in?
Exactly.
Okay, yes, that I don't exactly know. So I have not calibrated the kind of number of photons going in. And it's okay, it's not really an amplifier because you're inputting something at gigahertz and you're getting out something at 500 megahertz. But I calculated that when you increase the power by 1 dB, then you get a bit more than 2 dB out. So the gain is roughly like 8 dB of gain. So you more than double your input signal, which is a bit less than what you get with the tupa, but I think this is also because of the short. So actually with this long pulse, it might be more. I haven't checked.
Okay, I think we have 2 more questions, one here and one here. I don't know which one is easiest to get to.
Could you comment on the kind of back action you expect from these kind of bolometers? Like, you're relying on things heating up. Do you expect quasi-particles or anything like that?
Yes. So, I mean, so I'm not entirely sure actually how hot the nanowire gets. So I don't know for sure what kind of thermal excitations I'm getting out of line. So if I would really remove this isolator, would that decay the T1? I'm not entirely sure, and that is something to check. But I think it should not be too bad. I can't give a better answer than that, but it doesn't get very, very hot.
Great, and then let's take the last question.
Hi, very nice talk. Can you comment on how does this method scale? Can you do frequency multiplexing? Can you have a 1,000 qubit chip and still not heat up the fridge?
Yeah, so the bolometer can be multiplexed. So then you would multiplex kind of here. So it is, I think it's kind of similar scalability. You need a bit more components than if you would just have many resonators and one amplifier. So you kind of need, because the bolometer is broadband and it only senses the temperature change, so it doesn't know which frequency the signal came at. So compared to the amplifier, you need kind of one Bolometer for each qubit. So in that sense, it's worse scalability, but not too much worse, because and the advantage is that you don't need the isolators.
Great. So let's thank Andreas again. So the next talk is a little bit special. The speaker could unfortunately not be here. So instead, there's a video. That's a 15 minutes video, which will play with the talk. Then afterwards, you're of course still very encouraged to ask questions, but since it's a video, it's not live. So instead, talk to the organizers. They will collect your email, and you can email to Liang Jiu for questions.
So
and
Liang Yu will reach out to you with the question and the email, and
yes.
that was like now the idea. Great.
Perfect. So let's hear Liang Yu.
Welcome to my talk. My name is Liang Yuchen, and I am a PhD student from Chalmers University of Technology. Today I'm here to talk about our work on achieving qubit readout fidelity at the threshold for quantum error correction without a quantum limited amplifier. This work is supported by the quantum technology team at Chalmers and the Wallenbach Center for Quantum Technology. And we collaborate with VTT to fabricate our device presented here. So first, let's begin with a quick overview of the device and experimental setup. Our device consists of 3 phase-frequency transmon qubits, each coupled to a respective readout resonator. And all 3 resonators are then coupled to the common Purcell filter that is embedded in the feed line. The measurements are done without a quantum limited amplifier in the readout chain. Here is the optical macrograph of our device. Our key results include achieving fast, multiplex, 2-state single-shot readouts with fidelity of 99.5% by exploiting the high energy levels, and a 3-state assignment fidelity of 96.9% with a 2-tone readout pulse. This is all done within 140 nanoseconds of readout time. The techniques we'll present here are robust and straightforward to implement in a state-of-the-art superconducting device for quantum computing. To characterize the device, we first look at this one parameter as a function of frequency. Our qubits sit at around 5.3 GHz, and their respective resonators are at 6.5 GHz. The peak of the profile here is the center of the Purcell filter, which is around 6.4 GHz. Then we took a look at each resonator more closely, and here an example of the resonator 2. This is the state-dependent readout response for qubit 2 being at 0, 1, 2, and 3 state. This measurement will be very useful in choosing the readout frequency in the later experiment that need to read out the high energy levels very accurately. To better understand and characterize the energy levels of a qubit, we prepare the 0, 1, 2, and 3 state, and then measure the evolution of the population as a function of delay time, like in a T1 experiment. We could extract the respective decay rate between each 2 levels and see how much we could gain from exploiting those for readouts. Here are our measured results, showing the ground state population P0 as a function of delay time when the qubit is prepared in 0, 1, 2, or 3 state. When the qubit is prepared in the 1 state, the evolution is simply just what we saw in a standard T1 experiment. The interesting part shows up when the qubit is prepared in the 2 or 3 state. The profile of decay is no longer purely exponential. To quantitatively understand these results, we need to solve the system-related equation of population P0, P1, P2, and P3 as a function of time. Here shows the solution for P0 when qubit is prepared in the 2 state. We can see that it's a combination of 2 different exponential decay with opposite signs, leading to a slowdown of the decay rate compared to the case where qubit is prepared in the 1 state. A similar structure shows up when the qubit is prepared in the 3 state as well, leading to an even slower decay rate to ground. Therefore, we can take advantage of this behavior to boost readout fidelity by reducing the error from qubit relaxation during the readout. Here shows a normal readout calibration sequence where the qubits prepare in either 0 or 1 state and then directly measured. One of the major contributions to assignment error will be then the decay from 1 to 0 state during the readout time. To mitigate this error, we implement the following pulse scheme known as shelving, detailed in this paper very recently. We insert additional pi12 pulse to transfer the 1-state population to the 2-state before the readout, while the 0-state will remain unchanged. Since then, the direct-to-0 transition is pressed by 2 orders of magnitude compared to the sequential decay rates, we could use the 1-state as a buffer before decay to 0 and count all levels that are not 0 as a result of 1 state as the initial qubit state. Therefore, we can have more time to distinguish the qubit before a decay could affect the result of our readout. This can be even further improved by going higher in energy levels, which is what we have done here with another pi2-3 pulse. Therefore, for the ground state, we'll remain unchanged and measure 0 at the end, but for 1 state, we'll end up measuring a 3 in the ideal case. We could also utilize the pre-selection protocol, which involve readout the qubit before the sequence starts to reject any instance in which the qubit is detected in the excited state from further analysis. This will filter out the effect of thermal or residual population that will lead to a systematic error in our results. Therefore, since the 1-state population is transferred to a 3-state with the additional pulses, we could expect a slower, non-exponential decay rate to 0 at a very short time scale as we previously observed. Therefore, in principle, we should gain an advantage in discriminating between 0 and any other high-energy state, which we can calculate the improvement by using this previous T1 measured results. Here, as it shows in the table, if nothing is done before the readout, it will incur about 2% of error when reading out the 1 state due to relaxation. When additional pi12 pulse is added, it could be reduced to around 0.05%, and even further to 10 to the minus 4% if another pi23 pulse is added as well. Therefore, in principle, we should achieve greater than 99% readout fidelity even without parametric amplifiers. For this technique to work even better, we could utilize a readout frequency that maximally distinguishes between 0 and all the other states. We can do this by plot one I and Q component of the S21 parameter on a 2D plane, as we see here. This is the distribution of the 0-state response with the sum of noise indicated here. And these are the response of 1, 2, and 3 state. Since in this configuration, the high levels are basically indistinguishable from 1 state. A decay from 2 to 0 will not affect the readout outcome, only one from 1 to 0 again. So we can combine them into a not 0 state. Here are our measure results. We can clearly distinguish the 0 and not 0 state response. We can then take a projection along the optimal axis that joins the centers of these two distributions and reduce the data to a 1D plot. By combining everything we have to pair and explore the high levels, we could achieve a 2-state single-shot readout assignment fidelity of 99.5%. The remaining largest error of 0.9% is still coming from measuring 0, given that the qubit is prepared in 1, which will include contribution from decay, imperfect state preparation, and readout-induced mixing. We could fit a Gaussian to our result and conclude that our ideal readout fidelity is 99.95%, if only the overlap error limits our readout, as shown here. We repeat this calibration measurement for a large number of times for all 3 qubits on our device simultaneously. Here, the plot shows the average assignment fidelity without and with the additional pulses. They show improvement from less than 98% to above 99% with the sharpening technique, reducing the overall error by 57% on average. So the improvement from our technique here is both significant and robust over a large number of measurement times. Something more to note here is the choice of readout frequency will make high energy levels indistinguishable from each other. But this two-level population could be important to identify leakage errors in algorithm or gate calibration. An improvement strategy, therefore, can be to add a secondary readout pulse that could distinguish between these high energy levels and also achieve a greater advantage over the single-tone readout. As a start, we can choose a frequency that at the dip for one-state response as shown here, where 1 and 2 state are maximally distinguished. 2 or 3 state can still be indistinguishable, and we can lump them together as the 2 tilde state. For the two-tone scheme, we could distinguish the 2 state, so another sequence to prepare and calibrate the 2 state is added here. We'll combine 2 readout tones in the single pulse and process the signal with standard frequency multiplexing technique. So in the end, we'll acquire 2 sets of results simultaneously from one measurement run. Frequency and phase of this secondary readout tone is fine-tuned in the presence of primary tone, such that the readout performance is optimized. On top of that, we can also transfer the one-state population to the 3-state before the readout, and then use 2 state as a buffer. Similar to previous technique, we could gain advantage over the standard single-tone readout. As a result, 2 states transfer to 1 state before the readout. So we can prepare the qubit in the ground state, we will still measure a 0. When the qubit is prepared in 1, we will end up measuring a 3. And when the qubit is prepared in 2, we should be measuring 1 at the end. Afterwards, we also need to combine the result from the 2 readout tones to see if they can agree on a final result that lead to a specific initial state. That's why we devised this truth table here. For example, if both results return 0, then the initial state is definitely at 0. If the primary result return a not 0, then secondary result could return either 0 at 1 or 2 tilde state. It must be either in 2 or 1 state initially. If they completely disagree, then the instance is discarded as overlap error, which count to about 0.1, which account for around 0.5% of the total measured shots. Another method to analyze the two-tone result is to utilize a machine learning algorithm. We combine the IQ data from each tone into a 4-element vector and then feed it into a forward neural network, which contains 2 hidden layers with 16 nodes in the first layer and 8 nodes in the second layer. Then I could output the probability for the qubit to be initially at 0, 1, or 2 state. The initial training of the network takes around a few minutes, and the classification is almost instantaneous. The reason why we favored FNN over other algorithms such as a support vector machine or nonlinear support vector machine is its scalability and better performance when discriminating more than 2 states, shown in this recent work by Benjamin Leonard here. It also outperforms the truth table we have discussed earlier, and the fidelity we report will be coming from the result using this machine learning approach. So here are the measured result of the 2 readout tone, and we combine them to reproduce the 3-state assignment matrix using the machine learning algorithm. Average of the traits here give us a 3-state single-shot readout assignment fidelity of 96.9% with a 2-tone readout pulse, achieving a significant improvement over the single-tone case, which is originally 94.9%. One special feature of this scheme is that the 2 state is less likely to be missed and identified as 1 state than 0 state, since 2 state is transferred to 1 state as a result of additional pulses It's more easily to decay back to 0 than be excited back up to 2. So to sum it up, with a device designed with a common cell filter, we have achieved a boost in signal fidelity of 2-state and 3-state readout by exploiting high channels and using two-tone readout pulse. All of this is done without using a quantum-limited parametric amplifier. These techniques are robust and straightforward to implement in any current state-of-the-art superconducting device for quantum computing. We'll continue to investigate the remaining errors that limit our readout fidelity, which include errors in state preparation pulses, excitation from measurement-induced mixing, and readout crosstalk and dephasing during multiplex readout. Further improvement include using neural network to optimize the readout pulses, integrate a qubit reset protocol for this to be fully compatible with the error correction scheme, and utilize the parametric amplifier to further boost our SNR on top of what we have done here. So this is the end of my talk. Here's a list of works from our quantum computing team at Chalmers that we will present at SQA conference. And we encourage you to look at them if you are interested in our works. Here's a link to our preprint of the paper that's currently on the archive. Feel free to take a look there for further details. Then you're always welcome to contact us if you have any comments or questions. Thank you so much for your attention.
Great. So now, if you raise your hand, we will have staff pick up your email, and then Liang Yu will reach out to you once the emails are transferred.
And probably one short addition, a colleague that was participating also in this work is also here. Sandoku, could you please stay up? So stand up. If there are any questions, you can probably ask also Sandoku during lunch break or something.
Okay. Then, with that, we go to the final talk in this session. So this is from Javier Cirillo. We will talk about Andreev's spin qubits, which is coherently manipulated inside a weak-link Josephson junction. Take it away.
All right. I'm very glad to be speaking today here. Let me thank the organizers first. I will be telling you about manipulation of Andreev spin qubits. Andreev spin qubits are a very recent addition to the qubit zoo. Andreev spin levels were first resolved only in 2019 by the group in Saclay. So Urbina, Potier, Leandro Tosi were involved in that work. And manipulation was only demonstrated last year in the laboratory of Michel Devoret in Yale. So I will be talking about manipulation with stirrup tones and Raman tones. But first, let me tell you I come from the Universidad Politécnica de Cartagena. We have a really nice campus by the sea, by the Mediterranean Sea. And I'm setting up a group there, so I'm looking out for people who are interested in working in not only in superconducting qubits, but also in protocols for quantum sensing in NV centers and trapped ions. And we're also part of a large alliance of 8 campuses across Europe, the European University of Technology. Okay, so I will be speaking mostly about these 2 works here, done in close collaboration with Alfredo Levi-Yeyati. Alfredo has been working on the physics of Andreev reflection and Andreev excitations for many years. He works in the Universidad Autónoma de Madrid. And, well, Andreev spin qubits arise in the context of Josephson weak links, which are essentially Josephson junctions where you substitute the junction with a large gap here. And the gap is bridged by a nanowire, a semiconducting nanowire. So this is a broad layout of the the circuit. Here we have a readout and control gates. And essentially the physics happens in this nanowire. So let me offer you an intuitive cartoon of what goes on, what are these excitations. So essentially, in just some weak links in the semiconductor, you can think of transport of single electrons. If you have just one channel, single electrons going through, when they reach the interface, they need to jump into the superconductor with another electron, so they leave a hole behind which is reflected back. And if phase and energy are adjusted correctly, then they will recombine on the other end, and the electron will travel on. So we have seen two instances of Andreev reflection. In essence, you can think of the system as a cavity where you have electrons and holes going back and forth, and you have modes that are part hole, part electron, right? So because they're part electron, part hole, their charge is essentially zero. They don't couple to charge noise, essentially. And well, they have well-defined particle number and spin. And it is the spin that we're looking or we're interested in manipulating now. So the first problem was the spin could not be resolved because, well, in the energy phase relationship they're degenerate, right? So Alfredo Levi-Yayati and Sungun Park proposed or looked into the possibility of splitting these states by means of Rashba coupling. So indeed, if you look at the dispersion relation within the semiconductor, you see that they are split thanks to this initial term. If you put an electric field that introduces this effective Rashba coupling, these are the proximatized superconductors on the sides. And indeed, the Fermi wave number is different for each spin, but this is not enough to split the energy phase relation. And this is so just because we're looking at the effect of a single channel. But if you look at two channels, then the splitting appears. So if you look at a transport or at the effect of a near-lying second channel, here there's hybridization, and this affects the group velocity of each of the two spin excitations, right? So with this new group velocity, then it was possible to show here, 2019, in the laboratory of Saclay, that this splitting was possible. So they were able to demonstrate transitions across the two doublets, so spin-conserving transitions, these two, and also spin-flipping transitions in red, right? So, okay, we have, let me mention, they were able to observe these transitions, but not intra-doublet transitions, no intra-doublet spin flippings. They have been observed later, but they're very weak, right? So they were able to resolve this structure, but not to manipulate them. And then, well, we started thinking of ways to introduce manipulation here by means of these couplings to higher-lying states. And stirrup, stimulated Raman adiabatic passage, is a very robust approach. So we started looking into it. I think the best way to understand stirrup is in terms of dark states, right? So if you have a spin-up state and you drive the other transition, the spin-up is not going to be affected. The same for the opposite state. If you introduce adiabatically driving on the other transition, then what happens is you're forcing the state to remain in the dark state, right? So if you're in this spin down and you start driving that transition, you can manage the state to take this other form, the dark state, for this other driving configuration, right? So this is the basics of stirrup, and we wanted to look at, well, could we implement this in this coupling scheme that we have here. So we have essentially a 4-level system, and it's necessary to introduce driving in 2 different frequencies. So we considered 2 different forms of driving, depending whether you're using gate or flux driving. The spin flipping transitions are more or less suppressed, so we were considering this configuration here. And you have to make sure that you have a Raman coupling in the system. And, well, in order to perform stirrup in this context, well, you start initially driving this red transition with less frequency, if you start, for instance, in the spin down state, and then introduce later a tone on the larger frequency so that you introduce this Raman coupling. The mixing angle between both states increases, and you transfer the state between one spin to the other, right? And then we performed numerical simulations with this. You have to be careful with the simulations because you have 2 frequencies here, so they have to be time-dependent simulations, or it's a time-dependent Hamiltonian, right? And we observed that in principle, with the constraints of these samples, it was possible in principle to implement state transfer from spin down to spin up, right? But as you can see, there's some leakage to the state 2 up, right? And this is due to this unavoidable, unwanted coupling here that is not necessarily resonant, but that is very close indeed to the state 2 up, right? So there's this small leakage here, and I will come back to this question later. But another thing that you have to be careful with is preparing the spin state, because you start with a highly mixed state. You have essentially 0.5% chance to find your excitation in the spin up or spin down, so you need to introduce pumping, right? So in principle, simply with a resonant coupling of this spin flipping transition, you can induce spin pumping, right, and prepare, for instance, the 1 down state. And we explored all relevant parameters, for instance, the detuning that you use. You see here 2 resonances. I'm plotting here the purity. So, of course, 2 resonances because you have 2 options, either to prepare spin up or spin down, right? And as you increase for a large value or for a large range of the Rabi frequencies, you can manage purification of your state, but you cannot, there's at least an upper bound to these Rabi frequencies, because then you have the effect of these unwanted transitions, and in particular, this off-resonant transition kicks in, and you start pumping population on both directions, right? So you end up with a mixed state again. We explored as well the effect of decay from the excited levels and of dephasing. And finally, we wanted to make sure that this worked all together, so both pumping and stirrup. So after pumping, you create a state rho 0. After stirrup, a state rho 1. We want to see transfer of the state into the orthogonal state. So, for instance, spin down to spin up. And for this, we chose as a figure of merit the trace distance, because, well, if it's 1, then you have managed both to cool your spin state or to eliminate the mixture of your spin, and to transfer to the orthogonal state. So we see that for a large range of parameters, this works, both the pumping and the stirrup. And finally, just to show that indeed stirrup is very robust, we show here the population transfer as a function of the strength of the pulses and the delay of one pulse with respect to the other. For a large range of parameters, this works fine. Population transfer is successful. And interestingly, here we show as well Raman driving, right? Because here we have no delay between both pulses. You're introducing continuous or simultaneous driving of both transitions. So this is the Raman oscillation. So at least 3 Rabi oscillations can be observed here. And this is indeed what was observed in the laboratory. So in the group of Michel Devoré, they were not introducing a first pumping pulse, so they were doing post-selection. Here I show the probability of starting in state up, for instance, and ending in state down. And these plots are the amplitude of the pulses of each of the 2 frequencies involved, right? So the purple and the pink frequency. And as you can see, indeed, in the diagonal, you could see Rabi oscillations here, which were reproduced with the simulation. Okay, so we have the recent birth of a new quantum platform. There's a lot of work to do. And for instance, I mentioned before leakage to the 3rd level. We recently proposed in the context of MV centers a mechanism to avoid leakage also to a 3rd level that appears in MV centers by means of effective Raman couplings. So this could be translated to Andreev spin qubits as well. Techniques from laser cooling of trapped ions could be interesting as well in the context of Andreev spin qubits. We have done some work in this direction recently as well. And finally, the transfer tensor method, which I developed a few years ago, is useful for the analysis of open quantum system dynamics. It has been applied in a number of contexts and could be interesting in order to understand the origin of the spin noise that has been observed in Andreev spin qubits. So with this, let me just put out the references to the works I've been talking about and some other references to other works. And I'm happy to take any of your questions.
Great. Thanks for a nice talk. Let's get some questions before lunch. Yes, there's one right there.
We see that in the Bolometer talk, they use gold palladium, graphene, and I see some other people use indium arsenide. And what material you use, and for what consideration you choose that material? Thank you.
All right, so thank you for your question. The first question was how this splitting is managed. This is done at zero magnetic field. It's an electric field that effectively introduces this Reisbach coupling. And the material is for the superconductor aluminum, and for the nanowire, it's indium arsenide. And the reason is simply, they managed to generate these nanowires with this material, and that was these are the samples that are being created these days. But of course, other materials are also possible. And Andreev physics has been observed also in other setups, in other samples, also in point contacts as well. So this is something that is not necessarily associated with nanowires, but in this case, for the implementation of the Andreev spin qubit, it was more interesting to have a one-dimensional system.
Great. Let's take a few more questions.
Thanks. A very nice talk. In your energy levels, you're showing 4 of them, and then later you show this global ground state, which is sort of out of the picture. But with 2 channels, there should be 8 total levels, I believe. So what happens to the other 3?
I didn't get the last part.
I said with 2 channels, there should be 8 levels total.
Right.
So what happens to the other 3?
So the levels have to be within the gap, essentially. If not, you're not going to observe them. But yeah, so essentially the dispersion relation is not necessarily telling you how many levels you have, there is, in essence, this self-consistent relation that has to be solved. And, well, it gives you some levels. If the energy is beyond the gap, then you're not going to observe them. So simply, it depends on how much space you have here. If the other excitations are up here, you're not going to see them. Sorry?
Every conduction channel has two
well,
Andreev states.
Okay, but this okay. So this you mean maybe the effect of these levels here, but this is completely out of the gap here. So the levels that, I mean, you can only observe this associated to this, and these one are not going to appear. So the second channel is only there to hybridize a bit, but the relevant channel remains the single one that you have. So it just bends the first channel, so to say.
Okay, I thought there was one more question over. No more questions. We have time for one more. People are hungry, so I guess then we thank all the speakers from this session.
All right,
thanks a lot.
Then let's. The same as it worked yesterday. We have 2 lunch slots. You find it on your badge. A poster session will start here at 2 o'clock. So we're now rearranging the chairs here. But you can bring your poster when you see we are finished, kind of. But please have it here like 15 minutes before the poster session starts. Have a good one. open, I think, for people that are joining late. Okay, so the next session will start soon, and for that, I'd like to introduce to you Adrian Rohe, who is chairing the next session. So please give a big hand for Adrian.
Thank you very much, Stefan. So welcome everyone to the session on algorithms applications. It is a pleasure to introduce the first speaker, Johan Pop from Karlsruhe Institute of Technology, who will be talking about quantum Szilard engines. Give a warm applause for Johan Pop.
Thank you, Mr. Chairman. Thank you to the organizers for the kind invitation to speak at this very stimulating conference I found so far. And I'm looking forward to the next talks and to the last day. Today, so my name is Johan Pop. I'm a researcher at the Karlsruhe Institute of Technology. And today it will be my pleasure to tell you about an experiment which utilizes quantum non-demolition readout of fluxonium qubit and real-time feedback based on the result of this readout performed in collaboration with our partners and friends from quantum machines. Szilard engine is very similar. It's part of the same class of systems as Maxwell Demon. So it relies, basically it achieves cooling or heating, in this case, of a two-level collection, right here, of a collection of two-level systems, simply by performing quantum information processing. Right? So that's the principle of operation in a nutshell. And as such, it requires an intelligent being to take the right decisions at the right times. And in this case, that intelligent being was the PhD student, Martin Spieker, who is not here, but who is always very happy to talk about this. So we have seen already quite a few talks about superconducting qubits and how you can classify them based on the different components and the different parameters of these components. So I won't spend too much time talking about this again. I think this was very well introduced already in the previous talks. As a reminder, we have three types of elements, right? A capacitor here in green, the Josephson junction, which provides the nonlinearity in blue, and an inductor, and they're all shunting each other, if you wish. And then the associated Hamiltonian is listed below. And then depending on whether you have all of these elements or not and their parameters, you can talk about a Cooper pair box or a transmon or a fluxonium or a flux qubit or a quasi-charge qubit. But what I do want to emphasize is the fact that all of these elements are made of materials, right? And I think I'm not saying anything that you don't know already. But what I want to emphasize is the fact it's the enormous complexity that comes with this fact. So you can have noise and losses in any of these materials, and it's often the case that you have them all together. Right? It's not just one or the other. It's 2 or 3 or even 4 mechanisms, sometimes contributing to similar degrees. So it's very difficult often to really disentangle what is limiting your device and what is the route to improve it. So in this goal of improving our devices, it is very important to find new ways of characterizing the environment and extracting useful information about what is happening behind this very simple Hamiltonian that we have here. So I would like to remind first a seminal experiment performed in the MIT group a few years ago, where this approach is beautifully illustrated. What they have done in this experiment with a flux qubit is that they simply applied a sequence of pi pulses, as you can see here, pi pulse, pi pulse, pi pulse, spaced apart by approximately T1 of the qubit, and T1 is the energy relaxation time. And what they saw is that depending on how many pi pulses they apply, you can see, as can be seen in this plot here, the relaxation time increases. So if you apply 2 pulses or, sorry, 1 or 4 or all the way up to 40, the relaxation gets slower and slower and slower, which indicates that T1 is increasing. Right? So this is very interesting, and it's if this is confirmed, right, this would be a magnificent way to improve your T1 by a factor of 5 or by a factor of 10, simply by pumping it and saturating maybe some loss mechanism or removing some loss mechanism from its environment. So we did the same experiment on our own fluxonium qubit, so a different kind of flux qubit. And you can see that we saw very similar behavior. So this was the starting point of the project. We saw that in our case also, if we apply 1 pulse or 5 or 10 or 50, we see a drastic slowdown of the qubit relaxation. And you might notice that I'm already starting to be hesitant to say T1, because I'm not, I think it's very easy and it's very reasonable to call this T1. But in view of what I know it's coming, the slides that are coming, I just don't want to call it T1 yet, and you will see why. I'll just call it relaxation, qubit population relaxation. So before I show you our experiments in detail and how we went beyond this first, how we improved, I think, and we went beyond this first principle demonstration from the MIT group, I just want to show you a bit how our qubit looks like, because it is a bit peculiar, I would say, and it hasn't been presented yet in the conference. So we are dealing with fluxonium qubits, so we need this inductor, which is highlighted here in red. We need it to be very large. And there are several ways. I will talk to you about 3 ways of implementing this superinductor. So as Vladimir showed yesterday, a very successful and a remarkably stable way of implementing it is by using Josephson junctions. And here I'm just showing an SEM image of one of the Josephson junction arrays that I fabricated for one of these qubits, right? So it's, there's a lot of literature and the field is very active, so it's really exciting. And I do want to take the opportunity to mention the pioneering work from Delsing and Heviland back in the 90s. Then there is a very exciting development recently from the IST group mainly, which shows that you can implement these superinductors in fluxonium qubits also using geometric inductors, right? Just using a spiral. And this is also very interesting, and there has also been some pioneering work from other groups in this field. And what is most relevant for what I'm going to tell you next is the third way of implementing the superinductor, which is using disordered superconductors, right? And here we also have several options, so we can use nitrides, niobium nitride, niobium titanium nitride, and many others. Actually, this is by far not an exhaustive list. And we chose, in our lab, we chose to use granular aluminum because it's a bit different from these homogeneously disordered nitrides, like the ones I mentioned before, because it has this granular structure. So it has these granules of a few nanometers diameter, which are pure crystals, and they are surrounded by an amorphous oxide matrix. So you can really see them as self-assembled Josephson junction arrays. And since my background is to implement fluxonium qubits with junction arrays, this felt like a very smooth transition into the field of superconductors with disordered superinductors with disordered superconductors. And I'm not going to say more about granular aluminum and its use for superinductors, but if you're interested, I invite you to look at these references. So how does it look like? Just for reference, I'm showing you an optical image here of a fluxonium qubit implemented with Josephson junction arrays. And each line that you see here, and you see a lot of lines, it is a Josephson junction. So in this case, there were about 100 junctions in this loop. And this is a zoom in of the central part of this 2mm antenna, which is the readout resonator. So when we implemented the granular aluminum fluxonium, we decided to keep the same circuit design. So we have an antenna that you can see here. And in the middle, you can already see that there is something. And you can see in this zoom in, you can see that the fluxonium loop now looks very boring. Right? It's very impressive to show a Josephson junction array because it shows control in fabrication. And if you've ever done fabrication, it gives you personal satisfaction to see this array of junctions which came out of the lithography. But the beauty of what I'm showing you now, it's the simplicity. These are wires, right? These are wires, and they do implement the same amount of kinetic inductance as the one that I'm comparing it to the left, right? This other junction array fluxonium qubit. And we use these granular aluminum inductors for the superinductor, as you see here, but also for the coupling inductance, galvanic here, and also for the readout resonator in these two sections. The junction remains an overlap junction, in contrast to the work presented yesterday by Dennis Rieger, where there was also no junction, right? It was a nano junction which was obtained also using granular aluminum. But in this work, we have a standard overlap SIS junctions for the fluxonium. So how does the experiment look like? Well, we have our two-level system here, and I think Vlad managed to make a very convincing argument yesterday that it's really a two-level system with some added benefits from the higher levels, but which are very well isolated. So we have our two-level system here, and then we apply a readout pulse, which bounces off our readout cavity. It goes through one of our homemade parametric amplifiers that you can read more about them here if you're interested. The reason why we use these homemade amplifiers is that they are rather large dynamic range, so we can apply a lot of power to the readout. And fortunately, our qubit is also power resilient, so we can do very fast projective QND measurements. And then based on the outcome of this measurement, we have a schematics here of Mr. Szilard, who decides whether to apply a pi pulse or not, right? This is our intelligent being who decides whether it's time to apply a pi pulse or not to keep the qubit in a given state, let's say the ground state or the excited state. In our case, the role of the being is played by the quantum machines instrument, which can do this in real time. And here I'm just showing a typical measurement result where we start on the left here. We start from a measurement of the IQ clouds corresponding to the ground and the excited state. And as mentioned yesterday also, because the frequency is around 1 gigahertz, we do have quite a significant thermal population. And then in the excited state, and then by selecting to prepare the excited state, we apply a pi pulse when needed, and then we go to 96% fidelity preparation in the excited state. I'm showing the excited state because it's the worst of the two. If I would show so for the ground state, we have 99 point something fidelity. So the ground state is easier because T1 also helps us there. The readout pulse is some 100 nanoseconds. With this, as you can see here, these are 2 sigma radius. So circles, so we have almost 6 sigma separation. And feel free to discuss with the quantum machine guys. I think the internal latency of the card is somewhere in the range of 200 nanoseconds. So what I've described to you here is basically one turn of the engine. Right? This is the engine going one cycle and doing something. Right? Definitely processing information. I mean, that's the role of the card. But as I will show you now in the following, it also does something to the qubit and to its environment. And in order to understand what I'm going to show you, let me define the procedure. So we start with what we call a stabilization sequence with some big number n, so with some big n number of steps, where we have readout and then conditional pi pulse, readout, conditional pi pulse, and so on and so forth. At the end, we have an initialization where we simply decide, independent of the stabilization, we decide whether we put the qubit in the ground state or the excited state. So we have all combinations. We can stabilize GE, and we can initialize GE. Right? And that's why we gave them different names. And then after that, we have qubit monitoring, during which all we do is perform repeated QND readouts every 2 microseconds to see what the state of the qubit is. And you can see a typical trace here. So basically, you see quantum jumps. Right? So here, for almost 50 microseconds, the qubit was in the excited state. Then it spends something like 80 microseconds in the ground state, and so on and so forth. So these are our results. So what I'm showing you on this plot is the qubit population, right, extracted from these IQ clouds, versus time after stabilization and initialization. Right? And in this case, we stabilized in the excited state. So we kept the qubit in the excited state during 1 or 10 or 100 or increasingly longer sequences. And then we monitored it, and you see the X scale is linear until 300 microseconds, and you will see why later we had to make the scale logarithmic. Right? And, so if we just do initialization in E, we get something that looks very similar to a T1 relaxation. And then if we move on with the number and we keep increasing the length of the stabilization, we see that it slows down, similarly to the pi pulse sequence that I showed you in the introduction. And then moving on and moving on and moving on, going to all the way to 10,000 pulses, we see that the qubit appears to be living longer and longer and longer and longer. So at first, when you see this, you're like, ka-ching, looking for a house on the Riviera, to early retirement. But then we're like, okay. Let's do a control experiment, right? So if this is truly T1, then what should happen is that after this stabilization in E, if we initialize in G, we should also see a slow, very slow relaxation. So basically, we should see a curve that starts in 0 and then very slowly, takes its time to thermalize. But that's not what we see. So unfortunately, we see quite the opposite. We see a curve that shoots up very fast and even reaches a population inversion at this point. You see we have a population inversion of 55, sometimes even 60%. So this clearly shows that what we've done is actually we have not increased necessarily the T1 of the qubit, but what we have done is that we have heated a two-level system environment. And that's the key point. This data is only consistent with a two-level system environment. Otherwise, you would never get population inversion. So we can look at exactly how that comes about because we have quantum jump traces, right? So we can actually look at the gamma up and gamma down rates. And if we add them up to get T1, actually T1 is constant. Right? So it doesn't depend on the number of, on the length of the stabilization. So we model, as I mentioned before, it would be to test and to see what new physics and what we can extract and what we can learn from this experiment. We model our measurements with simply by a qubit coupled to some very finite number, like 20, 50 two-level systems. And we have a very minimalistic model. We have a fixed spacing between the two-level systems and a coupling. That's it. So you have two fit parameters, actually. And then we put everything in a rate equation and run it. And we can get really nice agreement. So basically, this is the data that overlaps with the model here is the data that was used for the fit. And once we fix these parameters, we can plot the model for everything else. And it fits. Right? So we only fit the initial part of one curve, and it actually fits all the data set. And my final slide is really meant to show you that this is an engine, this is a Szilard engine, which uses information as fuel. Because at this point, you could think, well, but how do I know that when you apply all of these pulses and these readouts, you're actually not warming up your attenuators right next to the qubit, or some trivial element near your qubit. And what we can do is do the opposite, right? We can cool down the experiment and the qubit environment. And that's what we do. So that's what we've demonstrated. So if we do stabilization in G, you notice that again, we have what looks like a very long T1 right here, right? Initialization in G and then a very slow relaxation. If we prepare it also in G, but if we prepare in E, our population shoots down now. And we even get a non-monotonic. If you look here for 10,000 stabilizations, you even get a non-monotonic behavior corresponding to the overshoot and the population inversion in the previous slide, right? So your qubit population goes down, and then it comes back up, right? So these curves are just simply offset by 5%, as you can see here in the asymptotic limit for clarity, right? So yeah, clearly this is a very local TLS environment that we have discovered. So what else can we learn? Well, from our model, we can see that the intrinsic two-level system relaxation is basically nothing. So we can fit our data if we assume that the TLSs live forever. And actually, we have to assume that they live more than 50 milliseconds. I mean, if they live less than 50 milliseconds, we cannot fit the data. But if we say that the TLSs live forever, it's also consistent with the data. So I would say that all we can say is that it's definitely longer than 50 milliseconds. So these are not the TLSs that people usually report when you see anti-crossings, like in the group of Alexei Ustinov, and not only, when they see anti-crossings, and those TLSs live much shorter. They have a much shorter lifetime. And then what we can do is now take the knowledge that we have about this environment and see what is left, what other mechanisms are left for the qubit, and then we see that our qubit would be 90 or 100 microseconds if we didn't have this TLS environment. So we also can find out about the next limit in our coherence. And this is more of a technical detail for the experts. So the values that we fit for G and delta are listed here. They're in the 10 and hundreds of kilohertz, respectively, which explains why we don't see anti-crossings. We don't even expect to see anti-crossings, and our model does confirm that. So in summary, I think I have shown you that this Szilard engine method is very powerful to uncover this type of hidden environments, which may or may not be present also in your qubits, right? And in the case of our qubit, we have uncovered a very long-lived TLS environment, in which basically TLSs are lossless, as far as we can say. And last but not least, I would like to remind you that although the population of the TLS system, as you've seen, changes drastically, and we can calculate it gets very close to saturation, the T1 time of our qubit does not change, right? So this idea that you can saturate a very local TLS environment and get better coherence for a qubit doesn't work in that way, right? It's not such an obvious improvement mechanism. All right. And with this, I would like to thank you for your attention.
So we have time for maybe one short question. I see one over there. Right over there.
I can talk now. So how do you know that environment is
TLSs instead of like harmonic modes like phonones?
Yeah. So there's at least one obvious telltale sign, which is the fact that you can see directly from the relaxation, is that we have population inversions. Right? So we have population inversions, and we have non-monotonical decay curves. And then once you look at the rates, you can also see a telltale sign, which is the fact that T1 is constant, which is what you expect for a TLS environment. So if you have a harmonic oscillator, an environment of harmonic oscillators, when you populate them, you actually expect your T1 to decrease. Some kind of stimulated emission, if you want. Yeah. But we don't see that. We see a constant T1.
Yeah, I see. Thank you.
Yeah.
Then we are ready to go to our next speaker, T.H. Ko from the University of Toronto.
Hi, good afternoon, everyone. I'd like to thank the organizers for giving me an opportunity to speak in this fantastic conference. So my name is T.H. I am from the University of Toronto, the Matter Lab, under the group of Alan Asperguzis, and this work is done in collaboration with the Yale Quantum Institute. And today I'm going to talk about quantum iterative power algorithms. Apparently, from the schedules, I'm the only one talking in details about these quantum algorithms, but I'm trying to make it interactive and interesting. Recently, I have moved to LG Electronics, also based in Toronto, AM Lab, and I'm trying to start a new quantum computing research group, and I will tell you a little bit more about that at the end of my presentation. So suppose that one day we have, fault-tolerant quantum computer with unlimited quantum qubit resources and unlimited amount of quantum gates that you can apply. Then the very natural questions to ask would be, what is going to be a killer quantum applications, right, to use such a fantastic machines? And as you already seen from the first speakers of the conference, Pedros mentions that, quantum chemistry simulations will be very good explorations. Also, one of the founders, Jens from IQM, was talking about, betterness of the humankind, right? So, very good example will be simulating this super complicated chemistry compound called FEM cofactor. Probably some of you might not notice that this is a very important compound in the nitrogen fixation processes, which is dealing with carbon dioxide emissions in atmospheres and things like that, But if you really use the classical computer, it simply is impossible to simulate that compound with a given accuracy. But again, of course, with a quantum computer, this is not possible as well, as you know. But in this state-of-the-art research paper published by Google Quantum AI teams recently, they showed that with their approach, right, in order to simulate this compound, you still need millions of physical qubits. However, you already know that we only have a few hundred qubits or so at the moment right now. And so in this kind of a NIST era, hardware devices, we have to somehow use NIST algorithms, and we have recently published this in a review of modern physics. If you're interested, you can also have a look at that. And this is, I believe, is the most comprehensive review articles, spanning about 90 over pages or so. Again, I'm also excited to see some of the authors in the audience as well. But just to summarize, if you you are not familiar with this kind of algorithms, is that in general what we do is that we initialize your physical qubit in a state zeros, and then you have to use the answer circuit, right? And then afterwards, you make a projected measurements, and then you feedback based on the problems that you are interested to study. You will have different types of optimizations functions to optimize, right? And then this value is optimized using the classical computers, and which is then fed back to the quantum circuits as the parameters, right? And then this is repeated many, many times until you arrive to a particular solutions that you're interested. However, of course, this kind of algorithms have many different shortcomings, right? One of them is that these algorithms never give you theoretical guarantees of convergence. Right? You never know. So most of the computer scientists working in the field hate this a lot. But again, as a physicist, we have no choice, right? Because we are in a noisy devices, and we have to somehow use those algorithms. And one of the holy grails in the field is that we hope that we use NIST devices with NIST algorithms to show some sort of practical computational advantage over the best classical computers, right? This is what we want to do. Okay, so in this talk, I will try to tell you and explain you one of the newest algorithms that we developed in our lab. And in order to do that, let me try to go back one step back and I'll try to explain you what is the iterative power algorithms. The story is very interesting. One of the first author here, Michelle Insole from Yale, she was given a virtual talk at the University of Toronto, and I was one of the audience in her talk, and then I found the algorithm is super interesting. And so let me try this. Again, this is a lot of words, right? In short, what they're trying to do is they want to solve some sort of optimization problem, in particular, given an arbitrary potential well structures, right? So you can think of it as like a one-dimensional potential well, but it's all classical. Now, this potential has various structures, and now you ask what the question is then, can you give me a global minimum of this arbitrary shade potential? Well, and what they show is that with their algorithms, what they do is that they need to have apply this what is called this oracle functions repetitively to the initial guess functions. At the end, after repeating k times, what you achieve is that, surprisingly, at the location of the global minima, you will generate sort of like a data functions kind of things. So if you are interested, you can have a look at the paper carefully. And the entire problems, I have explained it in a very hand-waving way, but they are, the problem is entirely mapped into the metric product representations, and there they're trying to use that metric product representation to efficiently solve this problem. But anyhow, have a look at this, right? This is very, very fantastic in the sense that the amount of number of times that you have to apply to achieve the solution is basically a log n, right? So n means the size of the system that you're trying to solve. Anyway, so the point here is that, okay, let me also try to explain some of the differences that, you know, this is a lot of, say, buzzword. Also, you know, you have, in the literatures, we have power methods, we have imaginary time evolutions, and now we have IPA, right, integrated power algorithms, but it sounds like they are somewhat equivalent if you talk about it, right, because you just keep applying the same oracles many times, and you in the end, you resolve in the solutions. But then in power methods, what you do is that you are using these oracles as a complex functions, and you have, say, you prepare your initial guess function, which is sort of like having a non-zero amplitude towards the largest eigenvalues of these oracle functions. Whereas in imaginary time evolution, this oracle function is basically a form of Boltzmann distributions, right? And in IPA, the difference is that the initial density is simply a probability density distributions, and oracle functions can be any types of integrable continuous, basically it's positive functions. As long as you have that, you can achieve these solutions in a way. So this is kind of exciting, and that's how we try to come up with similar ideas in a quantum circuit as well. So the mission statements of our proposed quantum algorithms is that, you know, we want to come up with a quantum version of a similar IPA classical algorithms. And of course, I'm talking about variational quantum algorithms, right? Because we wanted to use noisy devices that are available right now. And then we have to show, of course, that we indeed achieve improvement over the existing near-term quantum algorithms. Right? Otherwise, then I mean, if you attain similar results as the existing one, then there is no point of proposing a new one. But of course, so then let me try to go back a little bit and tell you a little bit about variation of quantum imaginary time evolutions. To do that, let me tell you a little bit about quantum imaginary time evolution, which is widely used in classical simulations of quantum systems, right? Especially in quantum Monte Carlo simulations and things like that. So anyway. What you try to do is that you have this somewhat like a non-unitary evolution kind of things, right? Because you have typically a unitary evolution is come with a minus IHT. Now time is rotated, right, to the real dimensions, and so you have this Boltzmann distributions. And the trick here is that now this is non-unitary evolutions, right? But then you still want to run this dynamical evolutions in a unitary quantum circuit. So what you do is that you try to minimize these actions, right? These equations, these Schrodinger equations, in a sense. Okay, and say, okay, any change in this equations has to be zero, so that it will satisfy this with rotated Schrodinger equations. So again, I have already mentioned to you that we are looking into the variational quantum algorithms, and so our wave function is parameterized by the Answer circuit, right? And so as I mentioned earlier already, in the beginning we initialize all the qubit in 0, and like I say, depending on the Answer circuit that we use. And these data parameters can be a random one or the certain types of distributions. But again, based on these structures, right, you will have some sort of initial wave functions into it. And since we are varying these theta angles, right, which are the rotational angles in the presence of the Answer circuit, and then you go through a little bit of algebras, and you see that this is equivalent to basically solving these linear equations, right? And so basically you get a matrix, and then you have C vector as well. So, and then the trick is that, you know, to generate those A and C, what you do is that you use the Hadamard's circuits to generate those A matrix elements and the C vector elements. And once you have that, and then you solve for, in a classical computer, you solve for the solutions of this theta dot. That data, with the values of theta dot, then you use this approximate Euler solution or Euler equations, right, to propagate into the next time step. And that is when you arrive to the next set of theta parameter, new theta parameters, and you then update into this variational quantum circuit. So just to give you a flavors, right? These are the expressions, and this is the general circuit. But anyway, okay, just to give you a flavor, how you will obtain a particular matrix element, for instance, A4, 9, and we are using very simple, say a rotational gate like R1 and coupled with control NOT gates and things like that. And so 4, 9 basically meaning is theta 4, right? And then also theta 9 here. And as I have shown you earlier on, the way you achieve that is basically equivalent to bringing down the generators of this rotational gate here, which is one gate, and it will be control Y and in front of this theta 4, as well as theta 9 is also similarly is doing this action here. And again, in here, I have make a remark about quantum dreaming stream. It's simply because this is, easy to do if you have a small circuit. And I'm talking about like theoretically, how do you simulate that, right? And you have to write a Python code and try to come up with this kind of quantum circuit, right? Depending on the matrix elements that you are trying to find. But then it is extremely complex. If your circuit size is really large, then you won't be able to use manual way. So what we do is that we represent entire quantum circuit as a string representations, and basically we cut the strings and insert additional string inside, and then we convert it back to the original quantum circuit again. Okay. Let me give you a take-home message. What is the D of this new proposed algorithm is that, as I mentioned earlier on, quantum imaginary time evolution is looking at the exponential of minus beta h, right? And now what we're saying is that, in fact, there is nothing to limit us to assume this particular functional form. If you choose other types of functional form that can give rise to the solutions much faster as compared to the exponential functions, then that functional form is also valid. And we can also always solve this non-unitary quantum Schrödinger equations in a digital quantum circuit using this Maclaurin variational principle. So one particular example that we used was to use a double exponential functions instead of exponential functions, right? And these are the new form of this A and C matrix and element C matrix. And there is some numerics that I would like to share with you. Here is a particular example of it's a tri models of Hamiltonian with 2 qubits. 10 minus Z0 and Z1, and we use the Y ansatz and YZ ansatz. Like, it doesn't matter what the form of ansatz, but as you can see, if you use the kite algorithms, quantum emergent time evolution algorithms, the evolution trajectory is in this way, and if you use our newly proposed one, then the time step you need to arrive at the desired solution is much shorter, right? And on the right-hand side, what you are seeing is different types of physical model Hamiltonians. In here, what we're trying to do is to find a ground state of a single flux tunable transmode Hamiltonian. And what we do is that we take this Hamiltonian and we map it into Pauli representations, and there we realize that you can only use 4 qubits to simulate this entire transmode systems. Anyway, if you are interested, ask me more about that during Q&A sessions. My time is almost up, and so as you can also see, the exact value of this ground state energy of the transmon is represented in the dashed line, right? And QINTE is if you use that, you will really require lots of time step, but if we use our algorithms, it converges quite pretty fast. Anyway, so that's going to be my last slide, and so of course. These proposed ones are fantastic and interesting, but all these families of emergent time like evolutions algorithms, they have 2 critical issues that make us extremely challenging if you try to use that in a practical real hardware devices. First one. Have a look at this, right? As I mentioned many times already, you need to figure out what are the A matrix elements and the C vectors elements using your quantum computer, right? Such that you will end up with this linear system of equations. And then, for instance, let me give you an example here. Right. Suppose let's look at the 2x2 matrix, and so C is this value, right? And from the quantum computer, you observe A is supposed to be this, right? The true ones are supposed to be this. And with this C value, you're supposed to get theta dot is to be a 2.8. However, due to the presence of noises, right, the metric elements that you obtain from the quantum computer is like differ by like this amount, right, small amount. But then if you try to find a solution theta dot, right, this is going to be extremely large. Right? So it has to do with condition number of these matrix elements A, and one has to. So we are looking into this extensions of these projects to try to bounce the errors in a quantum circuit such that the solutions obtained from these algorithms has to be reasonable, so that the propagations will be not so differ from the ideal scenario. Second problems with this is that, as I mentioned, we have to choose these propagations of Euler equations, and we have to choose delta tau, which has to be small. But then we don't know what delta tau to be choose in our typical run of the algorithms, and it would be nice to come out with adaptive algorithms where you can, from the run of the quantum algorithms, you can feed it back and come up with optimal delta tau that you have to choose for the next time step. That would be optimal and fantastic solutions for these types of algorithms. With that, let me try to acknowledge my former supervisor, Alans, and collaborators, Vitters from Yale's and Michelin's, Brandon's, Pau, and Chom. Yeah, and if you're interested, this is our recent preprints on arXiv that we posted on 22nd of September. With that, let me end my presentation by saying we are hiring and at the beautiful cities of Toronto, and we are recruiting for quantum algorithms and quantum AI research teams, and at the moment we already Yeah, I just moved like 3 weeks ago, and we have already have a substantial amount of members already. And if you're interested, yeah, please feel free to let me know. Thank you all for your attention.
Thank you very much for this talk. We are running slightly late, so if there's only one short question, that would be good. Then maybe the big one, we're slightly behind. Is that in the back a short question?
Thanks for the talk. So I was just wondering, like, if you compare it with this quantum natural gradient or the parameter shift for calculating the gradients, how does it scale up, or like how does it compare with those two algorithms?
Right, right. So this is different. So the quantum gradients and parameter shift rule, they are talking about finding the gradients of that wave functions, right? Here we are talking about finding the so basically these expressions here, right? These expressions, it is, if you think about it, this is equivalent to doing the Hadamard test. That's what I'm written down here. So yeah, so it is kind of equivalence, and you don't need to use this parameter shift rule and all this. So parameter shift rule will be important when you only see one side of the wave function has a derivative, and on the other side you don't have that. Then in that case, then it is it's kind of useful. But in our case, we have to do derivatives on two sides.
Good. Then I would like to give the floor to our next speaker, Pascal Stadler.
Here you go. And one quick announcement. If you leave the room, please close the door gently. That would be great. Thank you.
Yeah, so thank you for the introduction and also for giving me the possibility to present the work from HQS here. So I am working at HQS, which is a startup based in Karlsruhe in Germany. And today I'm going to present the approach that we developed to solve systems on a quantum computer that are very hard to solve on a conventional computer. And so there are a few problems that are that have an exponential speed up when they are solved on a quantum computer compared to a conventional computer. And one of them is time evolving a state under an Hamiltonian. So if we have a state psi at time t0, and we would like to know what is the state at time t, a quantum computer can do this exponentially more efficient than a conventional computer. But so this means also that if we do this time evolution, that we have to get all the physical properties from the time evolution. And if we are interested into other properties, like, for example, equilibrium state, then we also have to simulate the system how it is in nature, which means that we have to simulate it as open quantum systems. And on a classical computer, it can be even more difficult to solve a open quantum system, because now we don't have to time evolve the state psi, but we have to time evolve the density matrix. And at HQS, we develop software that can solve these open quantum systems on a quantum computer. And that's what what I'm going to talk today. But let me first introduce you quickly to these open quantum systems. So usually these are described by a system that is coupled to a bath or environment. And the Hamiltonian can be described now by a two-level system, which is our system, HS. Then we have a sum of bosonic modes, and we have the coupling between the the system and the bath. So this is basically the bath. And this is in general very difficult to solve if you would like to know the time evolution of this Hamiltonian. But it's also important to note that all the information that we need from the bath to solve the system properties is given by the spectral function S of omega. And the spectral function here is defined like here, so it contains the coupling between the system and the bath, so this Vk, and it also contains, for example, the frequency of the bath. And there are different kinds of these spectral functions. For example, they can be flat, and also they can be structured. And so at HQS, we are interested to solve problems that have a structured spectral function and are at finite temperature, because these are the problems that are very hard to solve on a conventional computer. And so the outline of our software is shown here. So this is like it's a complex software, and I'm not going to talk about every detail here. But let me also mention that there will be 2 papers about this software out very soon. And so if you would like to solve an open quantum system on a quantum computer, we can approach this problem from 2 sides. So on the left side, we have our actual problem. Yeah? So this can be, for example, a spin problem like NMR, or it can also be a photosynthesis, or it can even be a fermionic system. And so the first step that we then do is that we map this actual problem to an open system model. So this open system model I have shown you on the previous slides. And so in this step, basically, we extract our system Hamiltonian, so this HS, and also the spectral function. Then on the right side, we have our gate-based noisy quantum computer. And so if we would like to now solve this open quantum system, we need a model for that. And for this, we have developed an algorithm. And this algorithm we call the noisy algorithm model. And so what it basically does is that it describes how the device noise occurs in the simulated system. And with this noisy algorithm model, one can basically time evolve a density matrix, simulate the time evolution of a density matrix of a noisy quantum computer. Okay? And in the last step, then, we have to do the mapping. So we have to map our open system model to our noisy algorithm model. And so if we apply this software, so if we use it for a certain problem, then at the end, we will get a sequence of gates, and these gates, they could be basically directly applied to a quantum computer to solve an open system model. Okay, now today I would like to focus on this middle part. So I would like to describe a bit more detail how we map our open system Hamiltonian to the noisy algorithm model. So we will now assume that we have identified our system Hamiltonian, and we also know what is the spectral function. So let's see how we can map it to our noisy algorithm model. And so there are basically 2 steps that we have to do. So let's assume that for now that we have an ohmic spectral function. Yeah, so our actual problem can be described by an ohmic spectral function. And then the first step that we do is that, so we have here this ohmic spectral function, and the first step that we do is that we approximate the spectral function by a certain number of auxiliary broad bosonic modes. So which means that we write the spectral function as approximately equal to a sum of bosonic modes, and every bosonic mode has a certain frequency. It has a broadening and also a coupling between the system and the bath. So on the right side here, I show an example of this. So the black curve here is it's the ohmic spectral function. It has this exponential cutoff. Then we approximate it by 4 bosonic modes. So these are these blue 4 modes. And one can see that it fits. So the orange curve is the sum of these 4 bosonic modes, and it fits very nicely to our ohmic spectral function. So when we've done our first step and we approximated the spectral function by auxiliary bosonic modes, we go to the second step because we would like to run it on a quantum computer. So how we get it to a quantum computer is that we now represent these bosonic modes by spins. And so here's again shown an example. So we have here one system spin and one auxiliary boson. So on the previous slide it was 4 auxiliary bosons. And now we represent these auxiliary bosons by 2 auxiliary spins. And when we do this step, then we of course don't want to change the form of our spectral function. That's why we have to also modify the coupling. So since we write here every bosonic modes in terms of 2 spins, we have to scale the coupling by a factor square root of 2, 1 divided square root of 2. And then so the last step is that we have to do is that we have to then map the system qubits. So we have to identify the system qubits, the system spins, with the system qubits of our quantum chip, and the auxiliary spins are identified with sparse qubits, and we also have to identify the broadenings of these spins with the device noise. Okay, and then we can basically run the algorithm, and we can get the sequence of gates, and we could directly use it to run it on a quantum computer to model this open system model. Okay, now I will show 2 examples. These are just 2 simple examples that we done. So the first example is that we have a spin that is coupled to an ohmic path, and the second example will be about photosynthesis. So we now again assume that we know what is our spectral function. In this case, it's ohmic again. So we have again our ohmic spectral function here, and then we, in this case, we approximate this ohmic function by 8 auxiliary bosonic modes. So this is our first step. Then we, in the second step, we then represent these auxiliary bosonic modes by auxiliary spins. So we have here our system, 2-level system, and then we have these 8 bosonic modes. We represent it by 8 spins. So in this case, we represent every bosonic modes by a single spin. And then we can basically run, for example, look at basically the time evolution of our system spin. So these results are shown here. But before we do this, we have to also define some properties about our actual quantum device. So for example, we have to say what kind of 2 qubit gates are available and what kind of connectivity we have. And so in this case, we will assume that we have the Möllmer-Sørensen 2 qubit gate available, and we have all-to-all connectivity, but this can also be relaxed. And we have only damping noise. And so what I've shown here is the time evolution of the system spin when the coupling strength between the system and the bars increases. So for small coupling, we can see that we get damped oscillations. When we increase the coupling, we get strongly damped oscillations. And when we make it even stronger, we get a decay. So this should be not 0.1, but it should be 1.0. And here we compare then the result of our simulations with another method, which is called NIBA, which is for non-interacting blip approximation. And we can see that these 2 results of our simulation and the one from NIBA, they very nicely agree. But when we go to stronger coupling, so if we couple the system stronger to the bars, then we see that there is some deviation. And so basically the blue line does not lie exactly here on top of the green line. And so what we then also did was to look at what happens with NIBA when we now don't use the ohmic bars, but we use our approximated bars. And then we see that, okay, there is some deviation also from the exact result. So we know that basically one problem, so one error comes in because we fit our spectral function to bosonic modes. But then we see that there's still some deviation to our result. And this is because we represented every bosonic mode by just a single spin. Right, and to make this approximation more exact, we would have to represent every bosonic mode by several spins. Yeah, then one would get better result here. Okay, then I would like to show you the next example, which is photosynthesis. So in photosynthesis, usually starts with the absorption of a light, of a photon, followed by a transport of the excitation through a complex molecule. So this should represent the complex molecule, and then it will be, at the end, it will arrive at the excitation will be arrive at a reaction center, and at the reaction center, this excitation energy is converted to chemical energy. And so one way how you can model this actual problem is that, or you can represent it, is that by a number of two-level systems, they represent basically the excitation. So if there is excitation or not, which is coupled to an own environment. So for example, this would be a complex which is called the FMO complex, which consists of 8 big protein molecules, where every kind of two-level system is coupled to an own protein, which is a big environment. And it can also be that because this protein is very big, that there can be an overlap between the environments of neighboring two-level systems. So if you then write down our system Hamiltonian, it looks like this. So here we have not just one system spin, but we have several system spins, and they're all coupled to each other. And then we have here several baths, because every kind of two-level system is coupled to its own bath. Now, if we would like to simulate such an open quantum system, we can again proceed like in the previous case. So we again approximate the spectral function by auxiliary bosonic modes. But before we do that, we have to know what is the spectral function of such a system. And for that, we looked into literature, and a typical spectral function for this, it's again an ohmic spectral function. And in this case, we approximate it by just one bosonic mode, because it's a relatively high temperature. And in the next step, then, we have to represent these bosonic modes by auxiliary spins. So, and in the simulation that I will show you now, we assume that we have only 3 system spins, not 8, like I've shown on the previous slide. And every system spin is coupled to its own environment, which is just one bosonic mode. And then we do the step that we represent these bosonic modes by spins. And in this case, we represent every bosonic mode by just a single spin again. And then we can again look at the time evolution. So what we have done here is that we looked at how the excitation travels through the molecule to the big protein complex. So we have here only three two-level systems, and we insert at a certain time t0, we insert a excitation at two-level system 1, and then we will see how it evolves with time. And we can see that here after a certain time, the occupation of the level 3 increases. So it means basically the excitation has traveled from site 1 to site 3 in this environment. And if we also include correlations between the baths, so here if, for example, the baths 1 and baths 2 are correlated, then we can see that this transport is strongly suppressed. So here basically the occupation of site 3 is very low. So qualitatively, this is basically in agreement with results from the literature. Okay, and with that, I would like to thank you for your attention.
Good, we have time for a few questions.
Hi, thanks a lot for this very nice talk. So I have one question about this fitting, because the spectrum is complex. And what you show is you fit with this absolute value. How about this phase?
No, but I mean, it's, okay, I don't know exactly how to answer, but I mean, it's always real in this case, right?
But your S omega is a complex value function, right?
Okay, then I don't exactly know, yeah, but yeah, I don't think.
So I believe there was another question over there.
It was just me next to him. Hey, thanks for the nice talk. So you were, in your introduction, you were also speaking about how now the actual noise on the quantum computer kicks in, yeah? And you would also like to map it. So I just wonder how this actually comes about here in your simulations, whether you take it into account, effects such that you have decoherence of your spin, your system spins, intrinsically, because which would be on an actual chip, and how they come about here.
Yeah. So basically, this fitting will give you some broadening, right, of the bosonic modes, and this fitting and also of the spins. And then we map this broadening basic to the qubits. And this can be, for example, when you have superconducting qubits. I think most of the time we assume that we have decay and dephasing are the dominant noise mechanism.
Okay, and say if I don't want it in my model, can you do anything about it? Because it's intrinsically sitting there, right?
Yeah, I mean, we also looked at more general noise models, like, yeah, but this is something that I haven't looked into detail yet. Yeah.
Thank you.
So we have time for a few more questions. I see here on the front.
Thank you for the very nice thought. I'm simply because I'm not coming from this community. My question is, how do we know that this photosynthesis process has to obey a quantum mechanical model?
Yeah, there's also a big discussion about that. Yeah, so sometimes it's assumed that it's quantum mechanical, sometimes it's classical. Yeah, but this was just to show that this was just selected one open quantum system to show that we get nice agreement with results in literature.
But is your results equal to the sum of the experiments?
To what?
Can you fit your data to the experiments?
For no, we haven't tried that yet for photosynthesis. Only for the case that we couple it to.
Thank you.
Good. With that, please let's thank the final speaker of the session again.
On millikelvin electronics and other supporting technologies. So the next speaker is Florent Lecoq. He's going to present hardware for efficient measurements and scalable signal delivery in superconducting quantum processors. Let's give him a very nice welcome.
All right. All right, thanks everyone. Thanks for being here. Thanks for the organizers to give me the opportunity to start this session on supporting technologies. So I'm from NIST Boulder. We have a fairly large team that's here on the side. And what I'm going to try to do today, it's a little ambitious. I'm going to try to cover 2 topics in 20 minutes. And they both try to tackle some separate technological aspect of the scalability of quantum computers. So I'm going to first, the scalability challenge is kind of a fairly large topic. So I'm going to try to kind of narrow it down and tell you what part of it we're going to try to solve. Then I'm going to move on to talking about signal delivery using photonic links rather than microwave coax. And then I will switch gear and talk a little bit about non-reciprocal parametric devices and my kind of love-hate relationship with microwave circulators. All right, so obviously we all want to try to build larger and larger quantum computer, and the motivation is behind things like Shor and Grover algorithm, but even like this kind of nitrogen fixation problems. So in this paper, they kind of do a kind of in-depth estimation of how many qubits one would need to do that with quantum error correction overhead and so on. And you end up in kind of the million type number of qubits. Okay, so companies like Google or IBM have their roadmap, and you can tell in like a couple years, so I apologize, this is kind of not the most up-to-date roadmap they have. But still, it makes a point, like in a few years, they expect something between 1,000 and 1,000,000 qubits. That's kind of 3 orders of magnitude of uncertainty there. And that kind of highlights how difficult the problem is going to be. And so let's try to dig a little more and try to figure out what these roadblocks could be and what we can do about it. But for that, let's go back a little bit to something more basics. And I'm showing here the DiVincenzo criteria. Initialization for us is relatively simple. We just cool down to 10 millikelvin. Coherence, that's a work in progress, but it's already at a pretty interesting level where you can start doing some interesting quantum error correction. We use microwave signals to do both very high fidelity gates and good state discrimination. But even though I showed these nice little check marks here, obviously it's all like work in progress. Everybody's pushing these metrics further, and more importantly, are trying to maintain these metrics as we scale up the size of these processors. So that brings me to the fifth point, which is scalability. We've somewhat all taken that for granted. Lithographic fab, we can make large arrays of qubit already at 50 plus. But the overhead of the classical hardware is already starting to show up. So in that case, for the quantum supremacy paper, you can see all these coax that has heat load issues and space issues that fight against what we have available in our dilution refrigerators. And there were some actually nice estimation done at ETH Zurich on, with the state of the art that we have, how far can we scale that? And that goes pretty much up to like about 1,000 qubit or so. So how are we going to cover these 3 orders of magnitude to get to about 1,000,000 qubit? Well, I see 3 main options. The first one is to distribute to entanglement over multiple fridges. Imagine a quantum microwave network where you have your fridges as the nodes and some quantum channel between them. That can take the form of a microwave to optical converter. There's some fascinating work at Gila where using optomechanics, they've been able to get up to really surprising efficiency, close to 50% with just a little bit of added noise. You can take the approach of doing a fully cryogenic microwave link. That's also work from ETH Zurich with really impressive fidelity on the first try. Now these, quantum channels will really have really large reward when they work, but they remain a daunting challenge. So maybe we can go to something a little simpler, like make bigger fridges. That's a slightly modified picture of an IBM fridge. That's the GoldenEye fridge. Not quite sure what the cooling power is going to be, but it's going to be bigger than typical fridges. Okay? But there's even something even simpler, which is to just try to put more qubits in a given space, in a given fridge. So reduce your wire density, or increase your wire density, go to flexible superconducting coax, superconducting flux quantum coprocessor, even Cryo-CMOS, and we're going to hear about some of this work later in this session. The work I'm going to present really fits in that last category of trying to figure out how to pack more qubit in a single fridge. The first idea is try to figure out, can we go away from attenuated coaxial line and replace that with something else? That being a photonic link. So that's a very mature technology at room temperature for RF photonics. And the idea is really to just encode your microwave onto light, guide it down to a remote location, here the mixing chamber of a fridge, and reconstruct your microwave signal there. And the motivation is really almost purely to use optical fibers, because they are cheap and small, which is a good thing, but they have also terahertz of bandwidth and extremely low thermal conductivity. Now, we've all spent years already shielding our qubits from all sorts of stray photons. And here I'm talking about bringing literally microwatts of optical power in somewhat close vicinity from these devices. So it's a little bit of a crazy idea, and one can ask one question first: does it even work? And second, if it does, is it a scalable thing? So we've devised, to answer these questions, we've devised a proof of principle experiment with combining an electro-optic modulator at room temperature and an in-gas photodiode at the base temperature. You start with a laser at 1490 nanometer, modulate its intensity with microwave light, and you guide it to your photodetector that will reconstruct your microwave signal with full vector control. Now, what you do with that microwave signal is up to you. We chose to drive a 3D transmon with it. So either we can drive the qubit or we can drive the readout cavity. Okay? First things first, we're going to start by using that microwave to drive the readout cavity. So we go and probe its resonance frequency, and we measure the reflected signal with regular amplified microwave setup. And here, what I'm showing is really just a histogram of 40,000 homodyne measurements. And you extract from that a pretty good measurement fidelity of about 98%, which for us was exactly on par with what we would do with the regular coaxial line. So we can do high-fidelity single-shot QED readout, which is pretty good. And in the paper, we also kind of investigate, well, what happens to T1 or T2, and the answer is at the 40 microsecond level, nothing. So we've done at least that part properly. What we can do is then move that photodiode to a different part of the system to drive the qubit. So you warm up, you cool down, and you drive the qubit. So we drive on resonance, and we see Rabi oscillation, not very surprising. We can drive hard enough to get to Rabi rate of about 200 megahertz, which is way faster than what we'd need for regular transmons. And in the paper too, which I won't have time to really go into too much detail, we've also looked at the output noise properties of that photodiode and kind of the consequences on gate fidelities, for example. But this was mostly to show that it works pretty well. So is it a scalable thing? So for that, we're going to do kind of a little bit of a thought experiment. We're just going to take the cooling power of a fridge, 20 microwatt, and compare that to the heat load of each approach. And from that, ratio, we're just going to extract a number of qubits that one might be able to put in a fridge. So if you just take into account the passive heat load, fibers are kind of 3 to 4 orders of magnitude better. And if you imagine being able to put about 1,000 coax, you would be able to put about 1 million or a few million fibers in a fridge. Now, it's far from being the whole story. You have to take into account active heat load, so dissipation in the cold attenuators, or optical dissipation in the photodiode. And that becomes something, the total heat load now strongly depends on duty cycle, which is here at the bottom. For the coax approach, the solid line here is pretty much the same than the passive heat load. For the photonic link, however, it is by far the dominant source of heat load. One can think about increasing the impedance of the line to kind of squeeze a little more microwave power per optical power, and that's that second line here. But just to drive the point home, at around the typical duty cycle, about 1% that we could extract from previous work, that photonic link approach is already relatively competitive. Now, if you were able to devise an experiment that can run at lower duty cycle and still do something interesting, well, there is potentially a path to be able to drive hundreds of thousands, if not 1 million qubits. Now, for application where you're going to want to increase your pulse density to do quantum error correction, more on that side, the benefits are definitely not quite as clear. So to conclude on that first part, I want to say that this kind of delivery method can apply to other things like astronomy, detectors, 4K electronics. We're also working on the heat load. How can we reduce it, mostly increasing impedance or doing detection of short pulses. I will stress that this is not a quantum transducer. You cannot really do the coherent up conversion to optical frequency. And so we are also looking in other type of photonic links that could allow to do that, basically some very efficient EOM type thing. All right, so that's it for the first part. With the few minutes that I have left, I'm going to jump into the non-reciprocal parametric devices section. And here the idea is to go back kind of to the idea of the measurements for our qubits. And we all know kind of how it works. You end up with a dispersive readout, and you try to separate two histogram in IQ space. You start with a fairly low signal-to-noise ratio, usually because of the competition between the size of the drive signal and vacuum noise. And the idea is to try to maintain as much of it as you can with a low-noise measurement chain. These measurement chains look typically like this. You have your nicely coherent system inside a pristine environment, shielded from magnetic fields or stray photons. And your measurement signal needs to be amplified, usually in multiple stages, starting from a low-noise parametric amplifier. Okay, what we all end up having to do is go out of a shield to some circulators and back in, all that to protect our system from amplified vacuum noise. And that has some issues, right? So obviously the size, they're kind of like size of the wavelengths, so relatively bulky, which starts taking some space. But they're also very magnetic, and so not integrable on chip, which, for example, prevents us from exploring some interesting things like networks of qubit with non-reciprocal interaction between them. And then finally, they're relatively lossy, so that reduce your measurement efficiency, or in other words, corrupt the entanglement between your qubit state and your itinerant microwave field. That, in turn, reduce a little bit your measurement fidelity, but more importantly, it is the key metric if you want to do feedback, so feedback onto the system you were just measuring, or propagate that to another system for remote entanglement. So how can we fix this? Well, the idea is to basically have directional amplifiers that have really the non-reciprocity integrated in them so that we don't have to use any intermediate circulator. And I see mostly two avenues: traveling wave devices and multi-pump parametric devices. I should probably add here Bolometer after the talk this morning. I didn't have time to change that. So traveling wave devices, most of you use them. You have a strong pump that co-propagate with your signal along a transmission line and gets amplified. That's how you get intrinsically your directionality. You end up with gigahertz of bandwidth and large dynamic range. But the high pump power and the residual reverse gain that all these devices have so far, as far as I know, prevented the direct integration with a qubit without an isolator in between. So there are people working on that. And there's definitely a lot of interesting things to do. But that's not what we focused on at NEST. We actually went the other way, parametric non-reciprocity. And so the idea is really starts from a circulator, how it works. You have 3 ports that makes an interferometer. And then you have a non-reciprocal phase shift depending on which direction you circulate. And from these 2 ingredients, you end up with a directional non-reciprocal device. Okay? What we're going to do is very simply just reproduce that with a loop of superconducting resonators with parametric mixing element between them. Okay? That led us to build what we call the field programmable Josephson amplifier, or FPGA for short. And it looks like pretty much 3 LC circuits in parallel. Okay? You have one tunable inductor that participates in all the 3 normal modes of the system, A, B, and C. So I can modulate that inductor, let's say at the difference frequency between mode A and B, and I get a hopping term or a frequency conversion term. Okay? I can also pump at the sum, and then I get an amplification term. Okay? What's really important to remember is that because it's a parametric process, one carry the pump phase. And so you get a different phase up converting or down converting. That's your non-reciprocal phase shift. That's ingredient number 1. Now I can do that based on frequency with any pair of modes, or with 3 pumps. I can do it with all of them at the same time. And now I've built my interferometer with 2 paths from A to C. Okay? So that was my second ingredient. And in principle, I'm good to go. I'm going to have a directional device. Okay? So in practice, we don't do tunable inductor like everybody else. We do some sort of Josephson-based element, here a squid, and the knob's going to be the flux through the squid. We make these devices out of our own niobium tri-layer fab with low-loss dielectric, amorphous silicon here. I won't have time to kind of detail exactly what you're looking at here, but it's all in these references. Okay, we then place that in a diplexer. And the idea here is simply to map the different mode frequency to different physical ports, SMA connectors. Okay? Now, the reason we call it programmable is because I can set the scattering parameter of the system based on a set of pumps that I apply. If I apply nothing, it's an open circuit, no connection between input and output. With 1 pump, I can either get unity transmission both ways, that's a perfect frequency converter, or I can do the regular phase-sensitive or insensitive amplification. With 3 pumps, things get more interesting. I can break reciprocity and actually make a directional system, a circulator or an isolator. I can also, for different pump frequency and setup, I can do a directional phase insensitive amplifier. Okay? With a 4th pump, I can trade off that isolation for phase sensitivity and have the scattering parameter that resemble the one of a JPA on a circulator. And I'm not going to have time to show you all the different scattering of this device. It's all in these references. But I can show you that we can use it for good. I'm going to place it right at the output of a 3D cavity. And the signal flow will look like this. I send a signal, gets up converted to the cavity frequency, reflects off with a qubit state-dependent phase shift that then gets phase sensitively amplified toward the output toward more amplification. I can characterize that system by comparing the measurement rate, which is the rate at which your SNR grows with integration time, to the amount of dephasing that the qubit has incurred during that measurement. And from that ratio, we extract a measurement efficiency of about 72%, which is some of the highest reported in the literature. Now, in the future, we're moving toward better integration. We had kind of a piecemeal kind of setup where we took an existing 3D cavity and our amplifier and just connected them together. Now we're co-designing with the qubit really coupled directly to the input mode of that system. That turns into something that is more like a readout cavity with built-in directional gain more than just an amplifier. Okay, this is what the package looks like now. It's in the fridge. We don't have the data to show you yet. I hope to give you an update for SQA 2023. Now, just to compare and contrast and finish up, yes, these systems do not have the bandwidth or the dynamic range of a TUPA, but so far they are the first one that are fully integrable with qubits without a circulator in between. And then finally, they are definitely a little hard to use, so we're working on kind of making them a little more user-friendly for the future. So with that, I'd like to thank you for your attention, thank everybody in my group who's participated in that project, and I'm happy to take questions.
Thanks, Lo. Very nice talk. A question about the first part. If I understood correctly, for the microwave link at the bottom of the fridge, you're just driving directly with the photocurrent from the photodiode. Is that correct? So in this E to O to E conversion chain, have you looked at, or is there anything you can say about the phase noise that accumulates? Because this is now effectively the master clock for your qubit if you're using it to drive.
So You're talking about the phase of the laser light, right?
Well, it's ultimately the phase of the microwaves that you're using if you're driving your qubit with that tone.
So it's pretty much the same problem than without the photonic link. We have the same master clock issue with or without the photonic link. The photonic link does not really add any phase noise per se. It's really.
But sorry, I guess the question is, does the use of the photodiode to generate that microwave signal have a contribution of phase noise on top of what you start with?
No.
Okay, cool.
Yeah.
Hands here. Olli?
Yeah, kind of a continuation of the previous question, the same experiment. Now about the shot noise. So you said that increasing the impedance of the receiver would somehow make the power budget better, but I think the SNR is dominated by shot noise, which is kind of related to like the granules of electrons, and the impedance couldn't really help in that aspect.
I mean, you have the right point. Increasing the impedance will give you more power, but you pay the price of reduced SNR because it's all shot noise limited. And so we characterize that in the supplementary information, and that will eventually, increasing the impedance will reduce the potential gate fidelity you could get out of it.
And then Lior, over there.
Yeah, thanks for the great talk. Kind of following up on these questions. So is there basically a fundamental limit that you can say, that here you use certain amount of photons to generate and these photons all had to be dissipated, and this set the limit on your duty cycle, right? But how much can you push it? Like, can you get to a point where you could be close to 100%, or is there a fundamental limit on this technology?
So the sad truth about this is that these photodiodes are almost perfect. You pretty much get an electron hole pair per incoming photon. It's just the process itself, like how many microwave photons do you get out of these electron hole pairs. That is actually a nonlinear process, but it's mostly, that is what it is. There's not much more improvement we can do on that kind of technology. Like factors, maybe. Not orders of magnitude.
Okay, let's no, there is no more time, sorry. Super quick.
Yeah, thanks. Please, one. This photodiodes, you put it in microkelvin temperatures, millikelvin temperatures.
Yeah.
Millikelvin.
Yeah.
So they are working at millikelvin. Usually, the carriers do freeze out at such temperatures. Are there special ones? And they have to be small because this is very fast.
So all I can tell you is that in-gas photodiodes so far, every single one we've tested, from one that were made at Nest or purchased commercially, all in-gas photodiodes have worked out of the one we tried. The band gap moved a little bit, but they do not stop working. And they actually perform pretty much as well cold as they would at room temperature.
Perfect. Thank you again, Florette. Next speaker from the University of Tokyo is Yutaka Takeda.
Hi everyone. I'm Yutaka Takeda. I'm a PhD student in Yasunobu Nakamura's group in University of Tokyo. So I'm really excited to be here today to talk about our experimental work we've been working on for 3.5 years, and to realize a passive on-chip microwave circulator based on a Josephson ring. So let's get started. So to realize a fault-tolerant quantum computing using superconducting qubits, we have to keep increasing the number of qubits up to the millions. And so to do that, we have to think about how to scale up the whole system, not just the qubit array. including also including packages and the signal IOs and 3D integration and cryogenic setup, etc. So in this talk, I will focus on non-reciprocal devices such as isolators and circulators. So circulators is we need in typical superconducting qubit readout setup, we need a lot of circulators and isolators, which I'm showing in this picture. This kind of commercial ferrite circulator is quite bulky, and sometimes it's problematic because it produces additional loss. So, but we need circulators for signal routing and also protecting qubits from noise. So, so how can we downsize and hopefully integrate circulators for on-chip for larger quantum computers? So there have been several demonstrations of on-chip circulators, and I listed only some of them, and many of these are successful demonstrations requiring external RF drives, and which means we need to use additional RF input lines, which is limited resource in the additional refrigerator setup, and possibly it requires complex tuning procedures for individual devices. So the passive on-chip circulator is, if it's possible, it's more desirable for scalability. So the question is, the completely passive on-chip circulator is possible, and the answer is yes. So theoretically, in 2010, Jens Koch proposed this circuit. This circuit made from 3 linear resonator with Josephson ring coupler circuit, and this circuit will act as a circulator, and it's completely passive, so it's very nice, and it can be fabricated using the same process with usual superconducting qubits. We need only a linear resonator and Josephson junctions, so it's very nice, but it has been not realized experimentally yet. And we think there are 2 reasons for its experimental difficulties. The number one is it should be operated in charging regime, so which means this device will be vulnerable to charge noise, so charge-sensitive device. And number 2 is, so this device has some redundancy is in the circuit configuration as circulator. So there is a problem of shortage of tuning knobs. So in this work, we address this the second problem by modifying the original circuit to improve experimental feasibility. And I'm going to explain the modification which we propose. But before that, I have to explain how we can realize circulator in general. So as Florent nicely explained, so circulator can be modeled as an interferometer, and here I put a model. I use a model of ring resonator, but essentially this is an interferometer, and so this special ring resonator has 3 input-output ports at different coupling points. And so incoming signal from port 1, so port 1 will be coupled to, so there are 2 rotating mode inside this ring resonator. So the incoming signal from port 1 will be coupled to both of clockwise rotating mode and counterclockwise rotating mode. And then the interference of, as a result of interference of those two modes, at some special setting, the port 3 is completely isolated, and incoming signal from port 1 is will transmit only through to port 2. So to realize this, we need a special feature in this ring resonator, which is frequency splitting between clockwise and counterclockwise mode. So it's not usual, but if we realize this situation somehow, this system will work as a circulator. So, and in this case, the matching condition we have to satisfy is this equation. So the frequency splitting should be 1/3 kappa. Kappa is here external decay rate of ring resonator. So one condition. And so if we look at the Josephson ring circulator, I mentioned in the last slide, this circuit also can be modeled as this ring resonator model. So if we think these three resonator as a coupled resonator, but if we think these three resonators as a discrete version of ring resonator, there are two rotating and clockwise rotating and counterclockwise rotating mode, but there are another common mode which doesn't contribute anything to realize a non-reciprocity. So due to this common mode, additional common mode, the condition we have to satisfy to realize circulator becomes 2. So this is a kind of redundancy in this implementation. So we propose modifying the circuit configuration a little bit and achieve reproduce the minimum setup with 2-mode operation. So, yeah. So the original scheme was using 3 resonator. So let's think about this setting. There are 3 resonators without any coupling, so 3 different resonators. But if we think this is a virtually coupled resonator and discrete version of ring resonator, clockwise mode and counterclockwise mode and common mode is, of course, degenerate. And by making a coupling by this Josephson ring, Jens Koch have shown the effective resonator coupling can be complex values, and in the special setting, we can achieve this situation, and in this case, this circuit works as a circulator. But we have to tune this circuit to make this situation by using only a single tuning knob. That's the external flux. So we have only a single tuning knob. So by adding additional relatively large fixed value coupling between resonator, we can separate the common mode and use the common mode in frequency. So this is now much more like discrete ring resonator. So in this setup, we make a coupling with the Josephson ring. So we can make this situation, and so now common mode do nothing, and we can achieve a 2-mode operation of ring circulator. So this is our proposal. So by using this modification and to realize a two-mode operation, which improves experimental feasibility. Okay, so here I'm going to mention a little bit about the Josephson ring itself, and quickly. And this Josephson ring circuit used for realizing on-chip circulator, it can be regarded as a symmetric version of three-junction flux qubit. So in three-junction flux qubit, we need to approximate the Josephson two-dimensional Josephson potential to double well, isolated double well. So to do that, we introduce asymmetry in Josephson energy in three junctions, and that suppress charge, so-called charge-sensitive intercell tunnelings, and then we can make charge insensitivity. But if we take a completely opposite approach for this three-junction ring circuit, now it's fully charge-sensitive, but some special thing happened. So two plasmonic modes inside the deep well will be split in angular momentum basis due to the charge-dependent coupling with the shallow well fluxon state. So this plasmon mode can be used for splitting the ring resonator clockwise and counterclockwise rotating mode. So by using this Josephson ring coupler, this is what we expect for Josephson ring, and there are two plasmon excitation shown, this blue line and orange line, and these two modes split by applying external flux. Of course, we have to apply appropriate gate voltage, but these modes split in angular momentum basis, and they selectively couples to ring resonator mode, rotating mode. So it leads to rotating direction dependent dispersive shift for the ring resonator two modes. And in this case, we can tune the circuit only with a single external flux knob. And for example, if we have a 50 megahertz external kappa, what we have to do is just set the external flux to this point. If we have a 20 megahertz device, we have to set this point. This was impossible in original device. So we can absorb the fabrication imperfection or some error. So let's move on to the experimental part. So this is our device. We put three resonators with same frequency and added relatively large coupling capacitor between resonators. And at the center of the chip, we placed a Josephson ring. And one remark for this device is we need the threefold rotational symmetry of the system is very crucial in this scheme. So we had to use a special shape of Josephson junction electrode. So we usually use a 90-degree cross Manhattan-style junction, but in this case, I have to use a 60-degree cross Manhattan-style junction to improve symmetry. And then we measured non-reciprocity in this device. So basically, I measured forward transmission and reverse transmission and take the ratio between that. And what we observe is this. So vertical axis is external flux now. And in the red region and blue region, means there is a finite non-reciprocity observed. So there is a finite non-reciprocity, but if I calculate numerically, what should be seen is like this. So it's not same, but here if we think if I consider effect of charge parity switching inside a Josephson ring, I can reproduce the experimental result like this. So this is the expected result, and so we have a nice agreement with theory and experiment. And then we also observe two-dimensional gate voltage dependence, and also in this data we see a nice agreement with numerical simulation and experiment. And then this triangular pattern reflects effective total charge. So this blue region and red region correspond to effective total charge is the opposite sign, and the white region correspond to total charge number is 0. So, and this by acquiring this triangular pattern, enabling offset charge tracking for a long time, and I measured for 6 hours. There are slow drift, and sometimes it jumps within a few tens minutes lifetime. And then the most important characterization of this circulator device is this reflection and transmission spectra. And this blue line shows forward transmission, so it should be 0 dB, but there is a insertion loss around 3 dB, so compared to forward transmission and reverse transmission, there is a finite isolation around 7 dB. But this limitation of performance can be explained through by quasi-particle tunneling. So if there is no quasi-particle tunneling and also charge parity switching, this dashed line performance will be obtained. Okay. So, sorry. So with that, I will conclude my talk. And I talked about Josephson ring circulator. It's passive and on-chip. And we propose a new circuit configuration to realize two-mode operation. And I showed performance for this on-chip circulator. Yeah. Thank you for your attention.
Thank you, Yutaka. Time for 2 questions. Here, Francesco.
Yeah, so I was thinking about the rotational symmetry. Like the way I think of it, okay, there needs to be a symmetry in the EJs and the capacitances. Might matter where you put ground, but why is it important also, like that this is respected in space, that you want it symmetric in space?
Yeah, of course the effective circuit should be symmetric, but to realize that, the easiest way is make everything symmetric in real space. And yeah, that's the idea.
One last one. If not, we take
maybe I'll ask one. If you would, for example, take care of this charge sensitivity and some of the issues, if you allow yourself to dream a bit, what sort of bandwidth and isolation do you think you could get with a device like this?
Okay, so So as we see in this numerical simulation, the bandwidth is comparable, but isolation should be will not be limited anymore, and yeah, and power handling is also same.
Okay. Good. Let's thank the speaker again. Now from imec, we have Rohit Acharya. He will talk us about interfacing superconducting qubits with ultra-low power Cryo-CMOS Multiplexer at 11 millikelvin.
Hello, everyone. My name is Rohit Acharya. I'm a PhD candidate at KU Leuven, and I work with the Superconducting Quantum Computing Group at imec, which is also located in Leuven. Today, I'm very excited to be talking about our results about interfacing superconducting qubits with ultra-low power Cryo-CMOS multiplexer at very low temperatures of 11 millikelvin. I have to say that the first speaker, Lecoq, has made my task a bit easier by explaining a lot about the reason why we need to move towards scalable technology, but I will try to summarize the same in my own words. So all of us here are gathered because quantum computing promises significant computational advantage over classical computing to solve certain problems. And superconducting qubits, of course, are the leading candidates with some proof of principle demonstrations that we've heard about in the last couple of days. But what we've also heard in the last couple of days is the fact that we are not yet there to demonstrate true quantum advantage. What we need to do is we need to get better. So better in what terms? We need to get better at making quantum. That is, we need better qubits, better materials, fabrication techniques, and so on. But we also need to get better at showing the advantage that the quantum computing promises to deliver. And this includes maybe going to larger qubit arrays and demonstration of useful algorithms, like spoken in the previous sessions. This eventually boils down to be able to control, characterize, and read out a large number of qubits at millikelvin temperatures, which we normally do with a dilution refrigerator. But this is where, again, I would like to thank the first speaker because he's made the job easier. We have a problem with respect to scaling because of the limited input-output ports, which results in a bottleneck, and also because of the amount of, let's say, the thermal load that is being sent into the system because of the RF cables. How can we proceed? We can proceed in different ways. So first, one of the ways was already mentioned in the first talk, but I will take a slightly different path. What you can do now is actually try to move the measurement from room temperature to actually something within the fridge. And this is the realm of cryo-electronics and the related technologies. So this promises lower latency and noise, but however, it's in the context of superconducting qubits, it still has the same problem of having to wire the signals from these high temperature stages in the dilution refrigerator to the base temperature stage where our qubits will eventually sit. A significant amount of work has been done with cryo-electronics in terms of spin qubits where you can actually operate at high temperatures. What can we do then? So what we can do is think of a slightly different technique where we can have functional multiplexing to ease the I/O requirements of such systems. What are the demands of these functional multiplexing schemes? So what you need is to have a large operational bandwidth, low enough power dissipations to be able to operate at the millikelvin temperatures, provide high isolation between the ports, and also provide fast switching. So what we intend to do essentially is to reduce the number of lines that run from room temperature or cryo-electronic to our qubit chip by multiplexing either the control lines or even the readout lines. And this is a technique that has been in development for quite some time now, and there are different approaches that you can take to implement such a multiplexing scheme. So today what I'm going to be focusing on is actually the functional RF cryo multiplexer, which is based on standard industry using a Foundry-compatible or a Foundry manufactured multiplexer. So without further ado, I introduce our multiplexer. So this is a picture that you can see of the PCB that hosts the multiplexer chip and a micrograph of how the device looks like. So it consists of, it's an SP40 multiplexer, so it has a single, it's a single pole 4 throw, which means you have one common RF port which can then be routed between 4 RF ports, RF1 to RF4. On the left, you can also see the block diagram of the circuit in a more simplified format. Now, our multiplexer can be controlled in 2 possible configurations. So you have a certain number of ports which enable serial communication, or we also have 2 ports D0, D1 to choose between the 4 ports which enable on-the-fly control of the ports. So the multiplexer itself is designed in 28 nanometer commercially available technology. It's designed to provide high isolation, and we do this using 2 levels of series shunt switches. So that is what you can see here. These are basically big transistors that we have there. We also minimize the coupling between, on the PCB, from the mutual coupling between the ports on the PCB by implementing resonant LC structures using the bad capacitance and on-chip inductance, as you can see here. We also, the design also focuses on having low static power consumption, and this is done by using the minimum number of ESD cells that is required in the technology, and that is 4 cells. And we also have implemented faster switching by using a nonlinear bias transistor on the gate by using diode-coupled transistors. Right, so this is the multiplexer chip, and now I would like to show our quantum chip that we use to characterize the multiplexer. So this is a micrograph of the chip. So the more details about the fabrication were mentioned in the first talk in the first session of today by my colleague Anton, which you can refer for all the fabrication methods. But to summarize, what we have is a standard circuit QED architecture where we have a double pad transmon qubit with a single Josephson junction, which is then coupled to a readout resonator, which is then further coupled to a feed line for control and manipulation. As you can see, we do not have a flux line to control the qubit because it's not tunable, and we also do not have a direct microwave line to control the qubit states. All the required signals are sent through the feed line. This kind of a device is normally put in a setup, in a dilution refrigerator setup, which looks something like this, where you have the required attenuation. You send a signal to the sample, which is loaded onto the base temperature stage, and then you provide amplification and you measure the system. However, to be able to characterize our multiplexer, we modified the system slightly. You can see the modification here. What we did is we introduced a directional coupler, which gives us 2 possibilities to measure the qubit. So you have one, the direct line, which was already present to do standard characterization. But we also introduced another line, which is now routed through the multiplexer, which is loaded onto the base temperature stage of the fridge. And you have certain level of attenuation. Now, reason we have this attenuation, so you can also think of it as moving the attenuation which was before the multiplexer to after. And the reason is that we know that the electron temperature of these devices is normally higher than the phonon bath or the phonon temperature that you can have, because of which you can have a higher thermal radiation, and these attenuators work to ease this thermal radiation. That's reaching the quantum chip. Right, so what's the mechanism here? So what's happening is that we will use our qubit as a sensitive noise detector to measure the shot noise that is coming from because of this higher elevated temperature of the multiplexer. The higher elevated temperature will result in a slightly higher photon number occupation of the readout resonator, which then, due to the AC Stark effect, causes a change in the qubit frequency. And this fluctuation in the qubit frequency results in a dephasing, and by measuring the dephasing, we can quantify or characterize the multiplexer. And this is the approach that we use. Now let's jump into some of the experimental results. So I will start off with proving that you can use a multiplexer, first of all, at the base temperature, and then move towards more interesting qubit results. So like, again, starting with the power consumption. So here is a plot of the static power consumption that we obtain as a function of the bias voltage of the multiplexer at the base temperature. So you can see that we have a low power dissipation of about 0.60 microwatt at an operating voltage of 0.7 volt. At 0.7 volt, there is a slight increase of 1 millikelvin of the temperature, but over the entire range, up to 1 volt, you get a temperature increase of around 2 millikelvin. We've also tried to quantify where this power dissipation is coming from, and most of the power dissipation, approximately 60%, is due to the 4 static ESD cells that we have in the circuit. And normally the leakage path is actually through the large clamp diode, the clamp device that you have in the ESD protection cell, which tends to have a leakage from the drain to the gate and then through the NMOS in this particular technology node. We can also measure the dynamic power consumption of the circuit by switching dynamically the port D0 on our device, and we do this at 2 different voltages, at 0.7 and 0.9, as shown in the figure. Now, normally this scales quadratically with voltage, and this is what you see. So in a normalized aspect, you have around 1 picowatt per hertz of switching per volt square of bias. We've also tried to analyze further into where is this static dynamic power dissipation is coming from, and it's mainly because we tend to charge and discharge the capacitive nodes that are in the circuit. And around 75% of this dynamic power dissipation is coming due to the charging and discharging of the RF transistors that we have in our device. Nevertheless, what I would like to say here is that the power consumption is compatible with qubit measurements because we have less than a microwatt of power dissipation. But there also seems to be a path to reducing this number by reducing the threshold voltage of the device, and also by maybe changing the technology. But this is possible only if your RF performance is also matching your requirements. So let's go into the RF performance. I will start off with the port-to-port isolation, which is a measure of the leakage of signals between the various ports in the multiplexer. And what I show here is the port-to-port isolation measured between port 3 and the various other ports. As you can see, there is some sort of a frequency dependence, which is probably coming due to mismatches that we have when we measure in the fridge. But nevertheless, the isolation is at least 30 dB, and at some frequencies, it's even higher, reaching up to 40 dB. Also, in the inset of the plot, you can see the voltage dependence. So you can see that there is really a sharp switching at the threshold voltage of the transistor of the device. And beyond the threshold voltage, you don't really have a degradation in the performance. The other measure which is important to know is the insertion loss. So what is the loss coming in because of introducing the multiplexer in the device? And we've measured it over the spectrum of interest, and it's around 2.3 dB. It's not much of a concern because it can easily be compensated by sending higher power on the input line. And again, it shows that in the inset, you can see there is no significant change in behavior if you go beyond the threshold voltage. So the RF behavior also shows that we are compatible with qubit measurements. So then let's do the qubit measurements, right? So first, I will start off with showing the qubit lifetime as a function of the bias voltage. But here we don't use the signal routed through the multiplexer, but we route it through the reference input line, and you will see why this works. So this is the plot of the measurements of the qubit lifetimes obtained as a function of the bias voltage. What you can see here is that the T1 time of the qubit, which is around 30 microseconds, does not depend on the applied voltage. However, the T2 echo and the T2 star time of the qubit shows a drastic change after the device turns on. So it decreases from about 40 microseconds to around 25 microseconds at the operating voltage of 0.7 volt. We can further quantify this and find out what is the decoherence rate, the additional decoherence rate, in fact, coming because of this additional decoherence channel that our multiplexer introduces in the signal path. And we have estimated this, and it's shown in the figure here. And using the numbers that we have, we can actually estimate the effective temperature of the device, and it's around 150 millikelvin. Now, what does this all mean, right? So it means something in terms of limits of how much, at what power, or how long can you use the multiplexer. If instead of using a 13 dB attenuation, we had used a 20 dB attenuation, for example, the coherence time limit set by this decoherence channel would be 400 microsecond, which is quite large, and you're then not limited by the multiplexer. Now I would like to actually validate that our previous method, previous way of characterizing the lifetimes makes sense by actually measuring the lifetimes of the qubit via the multiplexer. And what you can see here is that the lifetimes are in fact the same as what was predicted from the previous plot. And therefore, it establishes our method of using the multiplexer just as a noise source and using the direct line to measure the qubit. This also makes it much easier to do the measurements because you don't have to worry about routing the signal through the multiplexer, especially in the case when you have dynamic switching. So again, how does now the qubit lifetime vary as a function of dynamically switching between the different ports of the multiplexer? And this is done now, again, using the reference line and by switching the multiplexer dynamically. So here is the plot of how the lifetime versus the switching rate. As you can see, the T1 time is still not affected, even with dynamic switching. However, the T2 times decrease further from the 25 microseconds that we had further up to 5 microseconds for a switching rate of almost 1 megahertz. We can do the same exercise and find out how the decoherence rate changes as a function of the switching rate, and this is what you obtain. We can do some back-of-the-envelope calculations as to how quickly do you need to switch in real-life experiments. And in the simplest case, where you don't have active reset and a good qubit of around 20 microsecond lifetime, this could correspond somewhere in the range of 100 kilohertz of switching, which will result only in a small additional dephasing rate of 10 kilohertz, which corresponds to 100 microseconds limit. And of course, if you want to switch faster, you can always have larger attenuation and still get better performance. Now I would like to show something very interesting. It's one of my last plots. It's the performance of it's the randomized benchmarking that we do under different operating conditions of the multiplexer. And I say it's interesting because this is the behavior that we obtain where I plot the randomized benchmark fidelity on the left-hand side, on the y-axis, as a function of the T2 times, which you obtain by varying the parameters of the multiplexer. What you can see is very clearly we have two different operating regimes. So we have one regime where you're really limited by the coherence time of the qubit, and it follows the coherence limit that you obtain by using a T1 time of 30 microseconds and our pulse duration of 40 nanoseconds. And then you can also see another limit that we have that is really a flatlining of the randomized benchmarking fidelity, which corresponds to the fact that we have limits coming from actually the measurement procedure, measurement calibration, pulse width constraints, and so on. So it's really a nice experiment so you can see the different, how different time scales matter. Nevertheless, I would like to point out that we have single qubit gate fidelities measured above 99.9% for nominal switching, for nominal operating conditions of the multiplexer. Just a quick note maybe, so this point here it's obtained for a dynamic switching of 5 megahertz at an operating voltage of 0.7 volt, which is also quite a large value. That brings me to my conclusion, and in view of time, I will just flash it here. The most important thing I would like to point out here is that we have shown that it's possible to reduce the operating voltage, and if you actually reduce the voltage to around 0.3 volt, you get a very low power consumption of 30 nanowatt in static case and 90 femtojoule per hertz in the dynamic case. Thank you.
Thank you, Roy. We have 2 minutes. Olli.
Great talk, thank you. Have you done, or are you planning to do any, let's say, dynamical measurements that you would see the effect of switching the transistor and then looking at the effect on the qubit or the readout resonator, like for a signal switch?
Yeah, so we have done some experiments, which is on the line. So it's actually doing a dynamic switching for controlling a pi pulse of the qubit. But in view of time, I could not show the results. But we really show that you can switch between the various ports dynamically on the fly as well.
Last.
Hello. Congratulations once again to show that cryo do work at millikelvin temperatures, CMOS cryo. My question is about improving the leakage. Do you think going to an FD-SOI will help? And the next question is, what is next? So when you scale up, this 4 is just a number here, right? We need hundreds. And the demultiplexer also. So what are your views going in that direction?
Right. Regarding technology, I think it's something that we tried out, and I think trying different technologies, different nodes obviously makes sense, and moving to FD-SOI is something also in the works within our design setup. The next question was about scaling up. Yes, of course, that really depends on the amount of power dissipation that you have. So, like I said, by reducing the threshold voltage, which maybe also FD-SOI helps to control the threshold voltage, you can actually scale it down to in the nanowatt range. It's not sure how low we can go, and of course, it depends on technology and so on. But with these values, you can already use a large number of ports. And the other thing maybe interesting also is that what I've shown is how the multiplexer affects the T2 times in the readout case, which is what you have. But in fact, if you use it for controlling the qubit, the drive line, then the limit is actually quite large. So even without attenuation, you don't expect any change in T2, but you can have a T1 limit of around 1 millisecond. So it's really a very good prospect to measure to multiplex control lines.
One last question.
This could be a very significant result, so congratulations. What's the best sub-threshold slope that you can get with your CMOS transistors at this temperature?
We've not characterized the slope itself, or what is the. But as you can see in the power dissipation, the plot which is actually flashing right now is quite steep. So as you can see here, it's actually quite steep. You go from. Yeah, like it's almost 2 orders of difference in the power, which is corresponds larger in terms of current. So I think the switching is quite fast, but we have not characterized how much exactly is the subthreshold slope.
The point is, because it's so much steeper than it would be at room temperature, 1,000 times in principle, you ought to be able to use much lower voltages, and thereby greatly reduce the heating load.
Exactly. So this is what also I think it can be done and should be done, is to really reduce the voltage. I gave a value for 0.3, but I mean, depending on the stability of the technology, you could scale it down even further.
Thank you.
Thank you.
Okay. One more thank to the speaker, and we close the session.
Then I just have some organizational announcements to make. I mean, how to better end such a great day about a lot of great with a lot of great scientific content, then with a conference dinner. So you're now all invited to join the conference dinner at 7 o'clock upstairs in the 2nd floor. But before you all leave, we first want to make a group picture with all of you. So please all come back into the room so we can make that picture. And please also gather in the middle then. In the meantime, I just wanted to announce, if you have registered with some dietary preferences, please at the entry of the restaurant take a dietary card so the staff knows that you are vegan or vegetarian or don't eat fish or whatever. Last thing, you can enter the restaurant at 6:45, so you can be there a little earlier and retrieve your